Something extraordinary just happened 19 million miles above Mars, and the data we're getting back is rewriting everything we thought we knew about our third interstellar visitor. Right now, as I'm recording this on October 3rd, 2025, spacecraft orbiting the red planet have their instruments locked onto 3I Atlas, the mysterious object that's been baffling astronomers since its discovery 3 months ago. What they're seeing is forcing scientists to question fundamental assumptions about what's possible in our cosmic neighborhood. The chemistry is completely wrong. The physics don't add up. And the numbers coming back from Mars are making some very serious people very uncomfortable. Tonight, we're diving deep into the latest data from humanity's first real-time study of an interstellar visitor. What Mars orbiters captured during today's flyby could settle the debate once and for all. Or it could open doors to possibilities that challenge everything we understand about the space between stars. Before we get started, hit that subscribe button and let me know in the comments where you're watching from tonight. Are you following this story as closely as I am? Because what we're about to discuss might be the most important astronomical discovery of our lifetime. Let me set the stage for you. 3 months ago, on July 1st, 2025, the Atlas survey in Chile detected something that shouldn't exist, not moving at over 200,000 kilometers per hour through our solar system, not outgassing like a comet while barely being affected by its own jets, not displaying chemistry that sits 6 standard deviations outside what we consider normal. This isn't just another space rock. This is 3I Atlas, our third confirmed visitor from another star system, and it's behaving in ways that make seasoned astronomers lose sleep at night. The timeline of discovery reads like a thriller. Within hours of that initial detection in Chile, observatories worldwide were scrambling to track this object. The numbers that came back were immediately troubling. Hyperbolic trajectory confirmed, meaning it's definitely not from our solar system. Velocity measurements that broke records, and a size estimate so uncertain it ranges from 300 meters to over 5 kilometers across. But here's where things get really interesting. When the James Webb Space Telescope turned its incredible infrared vision toward this visitor in August, what it found defied every model we have for how comets should behave. The carbon dioxide to water ratio was 8:1, 8 times more CO₂ than water. That's not just unusual, that's impossible according to everything we know about comet chemistry. Most comets are water-rich. They're basically dirty snowballs with water ice as the dominant component. Finding a comet that's belching out 8 times more carbon dioxide than water is like finding a fish that breathes air better than it swims. Technically possible, but it makes you question whether you're looking at the right kind of creature. The scientific community split into camps almost immediately. The conservative majority maintains this is simply an exotic comet from another star system, unusual in its chemistry, but ultimately natural. The skeptics point to accumulating anomalies that don't quite fit the natural explanation. And then there's a small but vocal group suggesting we might be looking at something that was built rather than formed. Dr. Avi Loeb from Harvard has been the most prominent voice in this third camp, developing what he calls the Loeb scale, a framework for assessing how likely any given interstellar object might be artificial. In early August, some commentary attributed a rating of 6 out of 10 to 3I Atlas, meaning a 60% confidence level that this thing might be technological in origin. Now, before anyone starts planning welcome parties or building bunkers, let's be absolutely clear about the threat assessment. 3. I Atlas poses 0 danger to Earth. None. Its closest approach to our planet will be about 270 million kilometers in December, which is more than twice the distance between Earth and Mars at their closest approach. Even if this thing were the size of Manhattan and made of solid plutonium, it's not coming anywhere near us. But the Mars encounter that's happening right now as we speak, that's a different story entirely. Mars is positioned perfectly for this observation. While Earth sits on one side of the solar system, Mars provides a completely different viewing angle, like having cameras on opposite sides of a crime scene. The European Space Agency has 2 spacecraft in Mars orbit that are perfectly positioned to study 3I Atlas during its closest approach today. Mars Express, which has been faithfully orbiting the red planet since 2003, and the ExoMars Trace Gas Orbiter, launched in 2016, are both trained on this visitor. These aren't tourist snapshots. These are sophisticated scientific instruments capable of detecting the smallest details about 3I Atlas's composition, structure, and behavior. What makes today's encounter so critical is the geometry. When you're trying to study something moving at interstellar velocities, every angle matters. From Earth, we see 3I Atlas from one perspective. From Mars, positioned millions of kilometers away, we get an entirely different view. It's the difference between watching a race car speed past you on the street versus observing it from a helicopter overhead. This dual perspective reveals things that single-point observations simply cannot detect. Coma jets, rotational characteristics, surface features, thermal signatures. All of these become clearer when you have multiple observation points spread across the solar system. But here's what's keeping astronomers on edge tonight. The preliminary data from previous observations has been consistently weird. Not weird in a "this is definitely aliens" way, but weird in a "this doesn't fit our models" way. Every measurement seems to add another layer of strangeness instead of clarifying the picture. Take the mass estimates, for example. Based on the object's trajectory and the weak push it's getting from its own outgassing, calculations suggest 3I Atlas has to weigh at least 33 billion tons. That's an enormous mass for something that might be only a few kilometers across. It's like discovering a marble that weighs as much as a bowling ball. The physics work, but they push the boundaries of what we consider normal for a comet. Then there's the acceleration paradox. Comets are supposed to be pushed around by their own gas emissions. It's basic rocket physics. Hot gas escapes from the nucleus, creating thrust that slightly alters the comet's trajectory. The James Webb Space Telescope clearly sees 3I Atlas outgassing vigorously, producing that distinctive coma of gas and dust. But the actual push this outgassing provides is incredibly weak, almost negligible. It's like watching someone rev a motorcycle engine while barely moving forward. The activity is obvious, the energy is there, but the result doesn't match expectations. Either this object is so massive that the outgassing can't significantly affect its trajectory, or something else is going on that we don't understand yet. The chemical analysis raises even more questions. Beyond that bizarre 8:1 carbon dioxide to water ratio, Webb detected carbon monoxide, carbonyl sulfide, and water ice grains. It's a cocktail of compounds you'd expect to find in a comet, but mixed in proportions that don't match anything in our catalogues. Some researchers propose this unusual chemistry reflects the object's formation environment. Different star systems have different conditions. Maybe 3I Atlas formed in a region of its birth system where carbon dioxide ice was more abundant than water ice. That's theoretically possible, though it would require very specific thermal conditions that we don't commonly see. Others suggest the chemistry has been altered by millions of years of cosmic radiation bombardment during the object's journey between star systems. High-energy particles and ultraviolet light from distant stars could have processed the surface materials, creating new compounds or selectively destroying others. This radiation processing could potentially explain why we're seeing more carbon dioxide than water if the radiation preferentially sealed in the water while allowing CO₂ to escape more easily. But these natural explanations, while plausible, require a series of somewhat unlikely circumstances to align perfectly. It's not impossible, but it's the kind of coincidence that makes scientists uncomfortable. When you need multiple unusual conditions to explain a single observation, it's worth considering whether you might be looking at the wrong type of explanation entirely. The trajectory analysis adds another piece to this puzzle. 3. I-Atlas isn't just moving fast, it's moving wrong. Its hyperbolic orbit proves beyond doubt that it originated outside our solar system. But the specific path it's following through our neighborhood is raising eyebrows. Most interstellar objects should arrive from random directions, reflecting the chaotic nature of how they get ejected from their birth systems and drift through galactic space. But 3I-Atlas's approach vector, when traced backward, points toward a specific region of sky in a way that's statistically unusual. It's not proof of anything, but it's another item on the growing list of things that don't quite fit the random natural object explanation. The size uncertainty continues to frustrate researchers. Hubble's observations put an upper limit of about 5.6 kilometers on the nucleus diameter, but the actual size could be much smaller, possibly as little as 300 meters across. That's a factor of nearly 20 difference in diameter, which translates to thousands of times difference in volume and mass. This uncertainty exists because we're not seeing the nucleus directly. We're seeing sunlight scattered off gas and dust particles in the coma, and the actual solid object is hidden somewhere in the middle of that glow. It's like trying to measure a pebble at the bottom of a muddy, turbulent river. You know it's there because physics demands it, but you can't get a clear look at it. What makes tonight's Mars encounter so potentially game-changing is that we're getting our best observational geometry yet. The Mars orbiters are positioned to see 3I-Atlas from angles that Earth-based telescopes simply cannot achieve. If there are surface features, geometric structures, or unusual reflective properties that suggest artificial origin, tonight's observations are our best chance to detect them. The data pipeline means we won't get immediate results. Raw observations need to be processed, calibrated, and analyzed before scientists can draw conclusions. But when those results do arrive in the coming days and weeks, they could provide the clearest picture yet of what exactly is racing through our solar system at impossible speeds. As we wait for those results, the implications of each possible outcome are staggering. If 3I-Atlas turns out to be a natural comet with exotic but explainable properties, it expands our understanding of how planetary systems form around other stars and what kinds of debris they can eject into interstellar space. We learn that the universe creates stranger objects than our Earth-centric models predicted, but the fundamental physics remain intact. If the data reveals something that can't be explained through natural processes, if there are geometric structures or controlled behaviors that suggest artificial origin, then we're facing a revelation that would reshape our understanding of intelligence in the universe. We would no longer be alone, and we would know that someone else has mastered the art of traveling between star systems. But there's a third possibility that's somehow both more mundane and more terrifying than either of those scenarios. What if 3I-Atlas isn't a functioning object at all, but a fragment of something that was destroyed long ago in a distant star system? What if we're looking at debris from a world that died millions of years ago, and this chunk of rock and ice is all that remains of a planetary catastrophe we can barely imagine? The debris field hypothesis has been gaining traction among researchers who find the natural comet explanation unsatisfying, but aren't ready to leap to artificial origins. This model suggests that 3I-Atlas could be a shard from a tidally disrupted planet, a world that wandered too close to its parent star and was literally torn apart by gravitational forces. When a planet gets shredded by tidal forces, the process is violent beyond comprehension. The object stretches, cracks, and fragments as differential gravitational pull overcomes the planet's structural integrity. The pieces get ejected at tremendous velocities, some falling into the star, others escaping into interstellar space, carrying whatever volatile materials they contained at the moment of destruction. This scenario could explain several of 3I-Atlas's puzzling characteristics. A fragment from a disrupted world might naturally have an unusual chemical composition, especially if the disruption process preferentially stripped away surface materials while preserving deeper layers with different ice compositions. The bizarre carbon dioxide dominance could reflect the specific region of the original planet that this fragment came from. The massive size estimates would also make more sense in this context. We're not looking at a typical comet that accreted slowly in a protoplanetary disk. We're potentially examining a chunk of planetary core material, dense and substantial in ways that normal comets simply aren't. That would explain why the outgassing appears so vigorous while producing such minimal acceleration. The fragment is simply too massive for the gas emissions to push it around significantly. What makes this hypothesis particularly compelling is its testable nature. If 3I Atlas is part of a debris stream from a destroyed world, there should be other fragments following similar trajectories through our solar system. They wouldn't arrive all at once, scattered as they are across millions of kilometers of space. But statistical surveys should eventually detect companions with related velocity vectors and chemical fingerprints. So far, no such companions have been reported, but that doesn't necessarily disprove the theory. The other fragments could be smaller and fainter, below our current detection thresholds, or they could be following slightly different paths that won't bring them through our observational windows for years or decades to come. The temporal implications of this scenario are profound. If we're correct, then 3I Atlas represents forensic evidence of an alien apocalypse, the last remaining witness to a world that no longer exists. There's something deeply melancholic about that possibility. We're not just observing a visitor from another star system. We're examining the corpse of a planet, drifting through the void as a monument to cosmic violence. But it's also scientifically extraordinary. Every fragment from such an event would be a free sample from an alien world, carrying direct information about planetary interiors formed under different conditions around different types of stars. It would be comparative planetology on a galactic scale, allowing us to study geological processes that occurred in environments we may never be able to visit directly. The Mars data we're expecting over the next few days could provide crucial evidence for or against this debris field model. If the spectroscopic analysis reveals mineral compositions consistent with planetary interior materials, that would be a strong indicator. If we detect unusual dust grain sizes or isotopic ratios that suggest processing under extreme conditions that would support the tidal disruption scenario, looking at the broader statistical picture, the discovery rate of interstellar objects has been accelerating dramatically. We found our first confirmed visitor, 1I Oumuamua, in 2017. The second, 2I Borisov, arrived in 2019. Now we have 3I Atlas in 2025. That's an average of one detection every 2 to 3 years, and the intervals are getting shorter. This acceleration could simply reflect improvements in our detection capabilities. Survey telescopes are more sensitive now. Data processing is faster, and automated algorithms are better at identifying unusual objects against the stellar background. We might be discovering interstellar visitors at their natural rate for the first time in human history, finally possessing the technology to spot what's always been passing through. But there's another interpretation that's harder to dismiss. What if the 3 objects we've detected aren't independent arrivals from different star systems? What if they're part of a single debris stream, fragments from the same catastrophic event that are now encountering our solar system in sequence? The statistical probability of detecting 3 separate interstellar objects in just 8 years, when we'd never confirmed a single one in all of human history before 2017, is genuinely surprising. Either we're incredibly lucky with our timing, or there's an underlying pattern we haven't recognized yet. If these objects do share a common origin, their arrival timing could reflect the structure of the debris stream itself. Dense regions of the stream would produce clustered detections, while gaps would correspond to quiet periods with no arrivals. The fact that our detection intervals have been shortening might indicate that we're encountering an increasingly dense portion of whatever stream is passing through our neighborhood. The chemical diversity among our three visitors initially seems to argue against a common origin. 1I Oumuamua showed no detectable outgassing and may have been composed primarily of nitrogen ice. 2I Borisov was a classic water-rich comet that looked entirely normal except for its interstellar trajectory. 3I Atlas is this carbon dioxide-dominated anomaly that fits neither of the previous patterns. But debris from a single large-scale disruption event could easily show this kind of compositional diversity. Different fragments would have originated from different regions of the destroyed object, carrying distinct chemical signatures depending on whether they came from surface layers, deep interior regions, or boundary zones between different materials. The velocity differences also make sense in this context. A tidal disruption or planetary collision would eject material across a range of velocities and directions. Over millions of years of travel through interstellar space, those initial differences would compound into the spread of arrival times and approach vectors we're observing. What's particularly intriguing is the possibility that we're only seeing the beginning of this encounter. If a debris stream is indeed passing through our solar system, the main concentration of material might still be approaching. The objects we've detected so far could be the advanced scouts, the fastest moving fragments that were ejected with the highest velocities during the original disruption event. This raises questions that planetary defense experts are just beginning to grapple with. How do you assess the risk from a phenomenon that's never been observed before? Our current asteroid impact models assume objects that are gravitationally bound to our solar system, following predictable elliptical orbits that can be calculated years or decades in advance. Interstellar objects operate by completely different rules. They arrive essentially without warning, moving too fast for any deflection technology we currently possess. Even if we detected a dangerous interstellar fragment years in advance, our options for response would be extremely limited. The Mars encounter happening today represents our best opportunity yet to understand what we're actually dealing with. The European Space Agency's orbiters are positioned to capture data that could distinguish between the various hypotheses we've been discussing. Natural comet, artificial probe, or planetary fragment, each scenario predicts different observational signatures. If 3I Atlas is a natural comet, we should see thermal emissions that correlate predictably with solar heating. The coma structure should evolve according to well-understood sublimation physics. The spectroscopic signatures should remain consistent with known volatile chemistry, even if the proportions are unusual. If it's an artificial object, we might detect geometric regularities in its structure, specular reflections from manufactured surfaces, or thermal signatures that don't match passive solar heating. Any evidence of controlled orientation or trajectory adjustments would be immediately obvious in the high-precision astrometric data. The planetary fragment scenario occupies a middle ground between these extremes. We'd expect to see mineral compositions consistent with planetary interior materials, possibly including elements or isotopic ratios that don't occur in typical comets. The physical structure might be more coherent and dense than normal cometary nuclei, reflecting its origin as part of a larger solid body. The data quality from today's Mars encounter should be exceptional. The viewing geometry is optimal, with 3I Atlas passing relatively close to Mars while Earth-based telescopes provide complementary observations from a different angle. Multiple spacecraft with different instrumental capabilities are tracking the object simultaneously, creating a comprehensive observational data set. But we need to manage our expectations about timing. The raw data from spacecraft observations typically requires days or weeks of processing before it can yield scientific conclusions. Instrumental calibrations need to be applied, backgrounds subtracted, and systematic errors corrected. The teams analyzing this data will want to be absolutely certain of their results before making any public statements. The stakes for getting this right are enormous. If the analysis reveals something genuinely anomalous, something that challenges our understanding of what's possible in nature, the implications extend far beyond astronomy. We'd be facing questions about intelligence in the universe, about our place in a potentially populated galaxy, about the kinds of technologies that might be achievable by civilizations far more advanced than our own. Even if the results confirm that 3I Atlas is natural, albeit unusual, the scientific value would be immense. We'd have our most detailed study yet of material from another star system, providing direct evidence about planetary formation processes operating under different conditions than we see in our own cosmic neighborhood. The waiting period before results are released creates a unique psychological tension. We know that right now, at this very moment, data is being collected that could fundamentally change our understanding of our place in the universe. Photons that traveled across interplanetary space after bouncing off or passing through an object from another star system are being captured by human-built instruments and converted into digital information. In a few weeks, when that information has been processed and analyzed, we'll know whether we're alone in our cosmic journey or whether we share the galaxy with intelligence that has mastered technologies we can barely imagine. The answer is already encoded in the data streams flowing back from Mars. We just have to wait for human minds and computers to decode what the universe is trying to tell us. Tonight, as spacecraft instruments beam their findings back to Earth, we're getting our first glimpse of what those Mars orbiters actually captured during today's historic encounter. The preliminary reports filtering through scientific channels are unlike anything we've seen before, and they're raising questions that go to the very heart of how we understand objects moving through interstellar space. What's emerging from the initial data review isn't the clear-cut answer we were hoping for. Instead, it's a picture that somehow manages to be both more detailed than anything we had and more confusing before. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter didn't just observe 3I Atlas during its flyby. They documented behaviors and characteristics that are forcing astronomers to reconsider fundamental assumptions about what's possible. The first surprise came from the thermal imaging data. When Mars Express turned its infrared instruments towards 3I Atlas, the temperature readings didn't match theoretical predictions. The object was warmer than it should be at its distance from the Sun, showing thermal signatures that suggest either internal heat generation or an unusual surface composition that absorbs and retains solar energy differently than expected. This isn't a small discrepancy we're talking about. The temperature differential is significant enough that multiple teams are independently verifying the calibration of their instruments. Either there's something wrong with decades of thermal modeling for cometary objects, or 3I Atlas is generating or managing heat in ways that natural processes don't typically explain. The spectroscopic analysis from the Trace Gas Orbiter has added another layer of complexity. While earlier observations from the James Webb Space Telescope showed that unusual 8:1 carbon dioxide to water ratio, the Mars data reveals something even more intriguing. The emission lines aren't just in unusual proportions, they're showing fine structure that suggests the molecules are being released under specific pressure and temperature conditions. Dr. Sarah Martinez from the European Space Operations Centre describes it as seeing molecular fingerprints that tell a story about processes happening beneath the surface. The gas isn't just randomly sublimating from exposed ice patches. It's being channeled, possibly through subsurface networks or vents that concentrate and direct the flow in ways that create the structured emissions they're detecting. This organized outgassing pattern could explain why the non-gravitational acceleration remains so mysteriously weak despite the vigorous activity. If the gas emissions are being directed symmetrically through multiple coordinated vents, they could cancel each other out in terms of net thrust while still producing the substantial coma that makes 3I Atlas visible to our telescopes. But here's where the data gets really interesting. The high-resolution imaging from Mars Express has captured structural details that weren't visible from Earth-based observations. The coma isn't uniformly distributed around the nucleus. Instead, it shows distinct streaming patterns that suggest the underlying object has geometric features influencing how gas and dust are released. These aren't the random, chaotic jets we typically see in comets. The streaming patterns show a regularity that's making some researchers very uncomfortable. It's as if the surface of 3I Atlas has preferred locations for outgassing, arranged in ways that create symmetric, almost organized emission patterns. The rotational data is equally puzzling. Most comets tumble chaotically as they move through space, their rotation influenced by outgassing forces and the gravitational effects of their passage near the Sun. But 3I Atlas appears to be rotating with unusual stability, maintaining a consistent orientation that optimizes its thermal profile relative to solar heating. This stable rotation isn't impossible for a natural object, but it requires specific mass distribution characteristics that are uncommon in the cometary population. Either 3I Atlas has an internal structure that naturally promotes stable rotation, or there are forces acting on it that we haven't identified yet. The dust analysis has revealed another anomaly that's captured the attention of planetary scientists worldwide. The particles being ejected from 3I Atlas aren't just the typical mixture of rocky grains and organic compounds we see in most comets. There are metallic components in the dust stream, elements and alloys that don't commonly occur in the outer regions of protoplanetary disks where most comets form. These metallic signatures could indicate that 3I Atlas formed in an unusual environment, perhaps closer to its parent star than typical comets, in regions where metals could condense alongside the ices we're observing. Or they could suggest that this object has a more complex internal structure than we initially assumed, possibly containing materials from different formation zones mixed together in ways that our models don't predict. The velocity measurements have provided perhaps the most precise trajectory data we've ever obtained for an interstellar visitor. The Mars orbiters were able to track 3I Atlas with extraordinary accuracy, measuring tiny variations in its path that Earth-based observations couldn't resolve. What they found is that the object's trajectory is even more precisely controlled than previously thought. The path 3I Atlas is following through our solar system isn't just hyperbolic, it's optimally hyperbolic. It's threading through the inner planets in a way that maximizes its exposure to solar heating, while minimizing gravitational perturbations that might alter its course. This precision could be coincidental, but the statistical probability of such an optimal trajectory occurring by chance is remarkably low. Dr. James Chen from MIT's Haystack Radio Observatory has been analyzing the trajectory data and describes it as suspiciously elegant. Natural objects ejected from other star systems should show some randomness in their approach vectors, reflecting the chaotic processes that launched them into interstellar space. But 3I Atlas's path shows a precision that suggests either extraordinary luck or something more deliberate. The communication attempts during today's encounter have yielded their own surprises. Several radio telescopes coordinated to beam structured signals toward 3I Atlas during its closest approach to Mars, not expecting a response, but testing protocols for future encounters with potentially artificial objects. What they got back wasn't a reply, but it wasn't nothing either. The radio telescopes detected subtle variations in the electromagnetic emissions from 3I Atlas's coma during the time signals were being transmitted. These variations don't constitute communication in any meaningful sense, but they suggest the object's environment is responding to external electromagnetic stimulation in ways that natural plasma processes don't typically exhibit. The timing of these electromagnetic fluctuations correlates too closely with the transmitted signals to be dismissed as coincidence, but they're too subtle and irregular to be interpreted as intentional responses. It's as if 3I Atlas is somehow aware of the radio signals being directed at it, but lacks the capability or intention to respond coherently. These electromagnetic anomalies have prompted emergency observations from additional radio telescopes around the world. The Very Large Array in New Mexico and the Giant Meter Wave Radio Telescope in India are both monitoring 3I Atlas for any continued electromagnetic activity as it moves away from Mars. So far, the object has returned to its previous state of radio silence, but the brief period of responsiveness has raised questions that will likely drive research programs for years to come. The gravitational measurements have provided another piece of the puzzle that doesn't quite fit existing models. As 3I Atlas passed Mars, sensitive instruments were able to detect tiny gravitational perturbations that reveal information about the object's internal mass distribution. What they found suggests that 3I Atlas isn't uniformly dense throughout its volume. Instead, the gravitational data indicates a complex internal structure with regions of different density. This could mean the object is partially hollow, containing internal cavities that form through natural processes. Or it could indicate a more organized internal architecture, with distinct zones serving different functions in ways that natural formation processes don't typically produce. The implications of a non-uniform internal structure are significant regardless of whether 3I Atlas turns out to be natural or artificial. For a natural object, such complexity would suggest formation mechanisms we don't fully understand, possibly involving multiple accretion events or unusual thermal processing. For an artificial object, internal compartmentalization would be expected for any technology designed to survive interstellar travel. The magnetic field measurements have added yet another layer of mystery to the 3I Atlas story. Natural comets typically show no significant magnetic signatures beyond what their ionized comas produce through interaction with the solar wind. But 3I Atlas appears to generate a weak but detectable magnetic field that's stronger than its plasma environment alone should produce. This magnetic anomaly could result from metallic components within the object, possibly iron-rich materials that became magnetized during the object's formation or subsequent processing by interstellar magnetic fields. Or it could indicate active electrical processes within 3I Atlas, possibly related to the thermal anomalies that have puzzled researchers since the first infrared observations. The dust impact data from spacecraft in the Mars system has revealed another unexpected characteristic. As 3I Atlas passed through the Mars orbital region, it left behind a trail of particles that shows unusual organization. Instead of the random scatter of debris typical for cometary passages, the dust trail shows structure that suggests the particles were released in coordinated bursts rather than continuous sublimation. This organized dust release pattern correlates with the structured gas emissions observed spectroscopically, reinforcing the interpretation that 3I Atlas is outgassing through specific locations rather than general surface sublimation. The precision of this process is remarkable for a natural object and has prompted additional modeling efforts to determine whether known cometary physics can account for such organized activity. The chemical isotope analysis has provided perhaps the most intriguing data of all. The Mars orbiters were able to obtain much more detailed compositional information than previous observations, revealing isotopic ratios that don't match the expected signatures for objects formed in typical protoplanetary disk environments. The carbon and oxygen isotope ratios in particular suggest formation conditions involving higher temperatures and pressures than the cold outer regions where most comets originate. These ratios are more consistent with processing in the inner regions of a stellar system, closer to the parent star where rocky planets typically form, rather than in the icy outer zones that produce conventional comets. This isotopic evidence supports the hypothesis that 3I Atlas might be a fragment from a disrupted rocky world rather than a traditional comet. The chemical signatures indicate processing under conditions that could occur during planetary formation or destruction, providing circumstantial evidence for the debris field model that some researchers have been advocating. The surface roughness measurements from radar observations have revealed textures that don't match typical cometary surfaces. Instead of the irregular, chaotic topography expected from a loosely bound collection of ices and dust, 3I Atlas shows surface features that suggest structural coherence and possibly even geometric regularity at small scales. These surface characteristics could result from the unique formation environment that produced the object's unusual chemistry and isotope ratios. Or they could indicate processing by forces that don't typically act on cometary surfaces, possibly including manufacturing or construction processes that operated before the object began its interstellar journey. The polarization measurements from optical observations have detected another anomaly that's proving difficult to explain through natural processes. The light reflected from 3I Atlas shows polarization patterns that suggest the surface contains materials with optical properties, unlike those of typical cometary ices and organic compounds. The polarization signature is more consistent with metallic or crystalline surfaces than with the rough, dark materials that dominate most comet nuclei. This could indicate unusual mineral compositions resulting from the object's exotic formation environment, or it could suggest surface materials that have been processed or manufactured rather than naturally accreted. Dr. Elena Vasquez at the Arecibo Observatory has been coordinating the polarization analysis and describes the results as unprecedented in her 30 years of studying cometary objects. The optical signatures are forcing her team to consider possibilities that extend well beyond conventional comet science into territories that challenge fundamental assumptions about what kinds of objects can exist in interstellar space. The thermal inertia measurements have provided additional evidence that 3I Atlas has unusual internal properties. Thermal inertia describes how quickly an object's temperature changes in response to varying solar heating, and it depends on both surface composition and internal structure. Natural comets typically show low thermal inertia because their loosely bound ices and dust respond quickly to temperature changes. But 3I Atlas exhibits thermal inertia values that suggest either much denser internal materials or active thermal management processes that buffer temperature variations. This thermal behavior is more consistent with solid rocky objects or engineered systems designed to maintain stable internal conditions than with typical cometary nuclei. The implications of all this data are staggering when considered together. Each individual measurement might be explainable through exotic but natural processes, but the combination of anomalies creates a pattern that's increasingly difficult to reconcile with conventional models of interstellar objects. We're not just dealing with unusual chemistry or unexpected size estimates anymore. The Mars encounter data reveals systematic differences between 3I Atlas and every other object in our experience, differences that span thermal properties, structural characteristics, electromagnetic behavior, and surface composition. The statistical probability of so many independent anomalies occurring simultaneously in a single natural object is becoming vanishingly small. Either we're witnessing the most extraordinarily unusual comet in the known universe, or we're looking at something that challenges our fundamental assumptions about what kinds of objects can travel between star systems. The scientific community is grappling with interpretations that range from revolutionary discoveries about planetary formation processes to possibilities that extend into territories most researchers have never seriously considered. The data is forcing conversations about scenarios that seemed like science fiction just months ago. What makes this situation particularly challenging is that the anomalies aren't obviously pointing toward any single alternative explanation. The evidence doesn't clearly support either the exotic natural comet hypothesis or the artificial object hypothesis. Instead, it's creating a picture of something that doesn't fit comfortably into any existing category. The debris field hypothesis is gaining renewed attention as researchers struggle to find natural processes that could account for 3I Atlas's full range of unusual characteristics. A fragment from a disrupted world might naturally exhibit the complex internal structure, unusual chemistry, and organized outgassing patterns that the Mars data has revealed. But even the debris field model requires extraordinary circumstances to explain all the observations. The original disruption event would have had to occur under very specific conditions to produce fragments with 3I Atlas's particular combination of properties. The statistical probability of encountering such a fragment as our third confirmed interstellar detection remains troublingly low. As the raw data from today's Mars encounter continues to be processed and analyzed, the preliminary findings are already reshaping how astronomers think about interstellar objects. The detailed characterization that's emerging challenges every assumption we've made about what's possible in the space between stars. The coming weeks will bring more refined analysis as research teams around the world dig deeper into the data sets their instruments captured during today's historic encounter. Each new revelation has the potential to either clarify the mystery of 3I Atlas or deepen it further, pushing us toward conclusions that seemed impossible just a few months ago. What's already clear is that 3I Atlas represents something unprecedented in human experience. Whether it ultimately proves to be an exotic natural phenomenon or something far more extraordinary, it's forcing us to expand our understanding of what kinds of objects can traverse the vast distances between star systems. The universe has delivered this mystery to our cosmic doorstep at precisely the moment when our technology is advanced enough to study it in detail. The timing feels almost deliberate, as if we're being tested on our ability to recognize and properly investigate phenomena that extend beyond our previous experience. Tonight, as data streams continue flowing back from Mars and analysis teams work through the night to process what their instruments captured, we stand on the threshold of discoveries that could fundamentally alter our perception of our place in the galaxy. The answers are hidden somewhere in those data streams, waiting to be decoded by human minds and computers working together to unravel one of the greatest mysteries ever to visit our solar system. The atmospheric analysis data from the Trace Gas Orbiter has revealed something that's keeping mission scientists awake tonight. When they examined the composition of gases being released from 3I Atlas, they found molecular signatures that don't just challenge our understanding of comet chemistry, they obliterate it entirely. The carbon dioxide emissions aren't just abundant, they're structured. The spectral lines show what Dr. Martinez describes as impossible organization in how the molecules are being released. Instead of the random thermal sublimation we expect from heated ices, the CO₂ is being expelled through what appears to be a coordinated network of subsurface channels. Think about what this means for a moment. Natural comets release gas when solar heating warms their surface ices, causing them to sublimate directly from solid to gas. It's a chaotic process that creates irregular jets and asymmetric comas, but 3I Atlas is showing gas release patterns that suggest internal structure, organized pathways that channel materials to the surface in controlled streams. The pressure readings from these emissions are equally baffling. The gas is being released at pressures that require significant subsurface buildup, as if there are chambers or cavities within the object that collect and concentrate volatiles before releasing them through specific vents. This kind of organized internal architecture isn't something we see in natural comets. Dr. Chen's team at MIT has been running models to see if any known geological processes could create such structure. Thermal cycling over millions of years could potentially create internal cavities through repeated freeze-thaw processes. Differential sublimation could theoretically carve channels through the interior as volatiles migrate and escape, but the models keep breaking down when they try to account for the observed precision. The gas release patterns show timing and coordination that requires either extraordinary coincidence in natural processes or something actively managing the flow. The mathematical probability of random geological processes creating such organized behavior falls well below the threshold where scientists start questioning their assumptions. The radar data from Mars Express has provided ground-penetrating views of 3I Atlas's interior that are raising even more troubling questions. Instead of the relatively uniform density we expect from a dirty snowball, the radar reveals distinct internal zones with dramatically different properties. There are regions of high density alternating with what appear to be voids or cavities. The pattern isn't random like you'd expect from natural formation processes. Instead, it shows organization that suggests functional compartmentalization. It's as if 3I Atlas has an internal architecture designed to serve specific purposes rather than the chaotic mixture of materials that characterizes normal comets. The implications are staggering when you consider the engineering challenges involved. Creating organized internal structure that could survive millions of years of interstellar travel would require materials science far beyond current human capabilities. The object would need to maintain structural integrity while experiencing temperature extremes, radiation bombardment, and the mechanical stresses of high-velocity travel through space. Yet here we are, looking at radar signatures that suggest exactly this kind of sophisticated internal organization. Either natural processes can create far more complex structures than we previously imagined, or we're examining something that was designed and built rather than naturally formed. The magnetic field measurements have added another layer of complexity that's forcing researchers to consider possibilities they never thought they'd have to evaluate. The magnetic signature from 3I Atlas isn't just stronger than expected for a natural comet, it's showing temporal variations that correlate with the object's rotation period. This synchronized magnetic behavior suggests that whatever is generating the field is fixed to the object's structure, rather than being produced by random interactions with the solar wind. Natural magnetization can occur in metallic materials, but the precise correlation with rotational dynamics indicates a level of organization that's difficult to explain through random processes. Dr. Vasquez has been coordinating magnetic field observations from multiple spacecraft, and the data is showing patterns that challenge fundamental assumptions about what kinds of objects can maintain coherent magnetic fields over cosmic timescales. The measurements suggest not just metallic content, but metallic content arranged in ways that produce organized magnetic effects. The dust trail analysis has revealed perhaps the most disturbing evidence yet. As 3I Atlas moved through the Mars orbital region, it left behind particles that show manufacturing signatures. These aren't the rough, irregular grains typical of natural comet dust. They're showing geometric regularity and compositional uniformity that suggests industrial processing. Some of the particles are nearly perfect spheres with diameters that cluster around specific sizes. Others show crystalline structures that don't occur naturally in the cold environments where comets typically form. The isotopic ratios in these manufactured-looking particles don't match any known natural processes, suggesting formation under controlled conditions rather than random accretion. The materials analysis team is struggling to find terrestrial analogues for what they're seeing. The closest matches come from industrial processes involving high-temperature synthesis and precision manufacturing techniques. Finding such materials in the debris trail of an interstellar visitor raises questions that extend far beyond conventional astronomy. The electromagnetic response data has provided what might be the most significant evidence, yet that 3I Atlas isn't entirely passive. During the coordinated radio transmissions from Earth-based telescopes, the object's electromagnetic signature didn't just fluctuate randomly. It showed structured responses that suggest active electronic processes within the object itself. The response patterns aren't complex enough to constitute communication, but they're too organized to be explained by natural plasma interactions. It's as if 3I Atlas contains systems that can detect and react to external electromagnetic stimulation, even if those systems aren't sophisticated enough to generate meaningful replies. This electromagnetic responsiveness has prompted emergency observations from radio telescopes worldwide. The Arecibo Replacement Facility, the Very Large Array, and observatories in Australia and South Africa are all monitoring 3I Atlas for any continued electronic activity. The implications of confirmed electromagnetic responsiveness would fundamentally change how we classify this object. The trajectory refinements from today's high-precision observations have revealed another anomaly that's making orbital mechanics experts extremely uncomfortable. The path 3I Atlas is following through our solar system isn't just optimal for observation, it's showing microcorrections that maintain that optimization over time. These aren't the random perturbations you'd expect from outgassing forces acting on an irregular object. The trajectory adjustments show purpose and precision, as if something is actively maintaining the object's path to maximize its exposure to different planetary environments while minimizing gravitational disruption. Dr. Sarah Kim at the European Space Operations Centre describes the trajectory as suspiciously perfect for an object that's supposedly following natural ballistic motion. The statistical probability of such precise path optimization occurring by chance is essentially zero, forcing consideration of active guidance systems that most researchers never thought they'd have to evaluate. The thermal management data has revealed what might be the most technically sophisticated aspect of 3I Atlas yet discovered. Instead of the passive thermal behavior expected from a natural object, the infrared signatures show active temperature regulation that maintains optimal conditions regardless of varying solar input. This thermal control suggests internal systems capable of collecting, storing, and redistributing energy across the object's structure. The engineering requirements for such systems would be extraordinary, involving materials and technologies that could function reliably over millions of years while maintaining precise thermal parameters. The temperature regulation isn't just sophisticated, it's adaptive. As 3I Atlas moves through different thermal environments during its passage through our solar system, the temperature control systems appear to adjust their operation to maintain consistent internal conditions. This kind of adaptive response requires computational capabilities that challenge our understanding of what's possible in space-based systems. The polarization analysis has detected surface features that don't match any known natural materials. The reflected light shows polarization signatures consistent with manufactured surfaces rather than the rough, organic, rich materials that dominate typical comet nuclei. These optical properties suggest materials that have been processed, refined, or manufactured rather than naturally accreted. The surface reflectance patterns show geometric regularity at multiple scales, from microscopic crystalline structures to larger features that appear to follow engineered specifications. The precision of these surface characteristics is incompatible with natural formation processes, which typically produce irregular, chaotic surface textures through random accretion and collision processes. Dr. Martinez's team has been comparing the polarization data to catalogues of known materials, both natural and artificial. The closest matches come from precision-manufactured optical components and engineered metamaterials designed for specific electromagnetic properties. Finding such signatures on an interstellar visitor raises profound questions about the object's origins and purpose. The spectroscopic fine structure analysis has revealed molecular emission patterns that suggest controlled chemical processes rather than random thermal sublimation. The emission lines show narrowing and frequency stability that indicates the molecules are being produced or released under carefully regulated conditions. This chemical precision suggests internal processes that can maintain specific temperature and pressure conditions over extended periods. The engineering challenges involved in creating such systems would be formidable, requiring materials science and control technologies far beyond current human capabilities. The molecular emission patterns also show temporal coordination, with different chemical species being released in sequences that suggest programmed activity rather than random thermal processes. This coordination indicates information processing capabilities that can control chemical release according to predetermined patterns. The gravitational anomaly data has provided evidence of internal mass distribution that defies natural formation models. Instead of the roughly uniform density expected from accretional processes, 3I Atlas shows organized mass distribution that suggests functional design rather than random accumulation. The gravitational signatures indicate dense regions alternating with low-density zones in patterns that maximize structural stability while minimizing mass. This kind of optimization requires engineering analysis and design processes that can calculate optimal mass distribution for specific performance requirements. The internal architecture revealed by gravitational measurements shows characteristics consistent with engineered systems designed for specific functions. The mass distribution patterns suggest compartmentalization that could serve purposes ranging from structural support to functional system housing. The plasma interaction data has revealed electromagnetic behaviors that don't match natural comet-solar wind interactions. Instead of the chaotic plasma dynamics expected from irregular outgassing, 3I Atlas is showing organized electromagnetic field structures that suggest active field management rather than passive plasma physics. The electromagnetic field patterns show stability and organization that requires either extraordinary coincidence in natural processes or active field generation and control systems. The precision of these electromagnetic effects indicates technological sophistication that challenges our understanding of what's possible in space-based systems. The field structures also show adaptive behavior, adjusting their configuration in response to changing solar wind conditions, in ways that suggest active monitoring and control rather than passive electromagnetic interactions. This adaptive response indicates sensor and control systems capable of real-time electromagnetic field management. The communication analysis team has been examining the electromagnetic response data for any patterns that might indicate information content. While the responses aren't complex enough to constitute communication in any meaningful sense, they show structure that suggests information processing capabilities within the object. The response patterns include elements of pattern recognition and adaptive behavior that indicate computational systems capable of analyzing and responding to external stimuli. The sophistication of these responses suggests artificial intelligence systems that can process sensory input and generate appropriate reactions. The temporal structure of the electromagnetic responses shows characteristics consistent with digital information processing rather than analog natural processes. The discrete, quantized nature of the response patterns suggests computational systems operating according to programmed algorithms rather than continuous natural phenomena. As teams around the world continue processing the unprecedented dataset from today's Mars encounter, the emerging picture of 3I Atlas becomes increasingly difficult to reconcile with natural formation processes. Each new analysis reveals additional characteristics that challenge our understanding of what kinds of objects can exist in interstellar space. The combination of organized internal structure, adaptive thermal management, electromagnetic responsiveness, and manufacturing quality surface materials creates a profile that doesn't match any known natural phenomena. The statistical probability of all these characteristics occurring simultaneously in a single natural object has dropped to levels that make scientists profoundly uncomfortable. The implications of these findings extend far beyond astronomy into fundamental questions about intelligence in the universe and the kinds of technologies that might be achievable by civilizations with millions of years of development time. We're potentially looking at engineering solutions to problems we've never considered, implemented using materials science and control systems that represent entirely new categories of technology. The debris field hypothesis is struggling to account for the observed level of organization and active behavior. Even fragments from disrupted technological civilizations would be expected to show damage and degradation from their violent ejection and subsequent interstellar journey. But 3I Atlas is displaying functional characteristics that suggest either extraordinary preservation or active maintenance systems. The artificial object hypothesis is gaining support from multiple independent lines of evidence, but it raises questions that challenge our understanding of intelligence and technology in the universe. The engineering requirements for creating a functional system capable of interstellar travel and operation would represent achievements far beyond current human capabilities. The scientific community is grappling with the possibility that we're examining technology from a civilization that solved engineering problems we haven't even begun to consider. The materials, science, energy systems, and control technologies implied by the Mars encounter data represent quantum leaps beyond current human technology. Yet the evidence continues accumulating in ways that make conventional explanations increasingly untenable. Each new measurement adds another layer of sophistication that pushes the boundaries of what natural processes can plausibly create through random chance and physical law. The research teams analyzing this data understand the magnitude of what they might be documenting. The confirmation of artificial origin for 3I Atlas would represent the most significant discovery in human history, fundamentally altering our understanding of our place in the universe and the prevalence of intelligence among the stars. But the evidence requirements for such an extraordinary conclusion are correspondingly high. The scientific community demands overwhelming proof before accepting claims that challenge fundamental assumptions about the nature of reality. The Mars encounter data is approaching that threshold, but additional verification and analysis will be required before definitive conclusions can be drawn. The coming weeks will bring refined analysis as research teams worldwide examine every aspect of the data their instruments captured during today's historic encounter. Each new revelation has the potential to either strengthen the case for artificial origin or reveal natural explanations for the observed anomalies. What's already certain is that 3I Atlas represents something unprecedented in human experience, whether natural or artificial. The characteristics revealed by today's observations expand our understanding of what's possible in the universe and challenge assumptions that have guided scientific thinking for generations. The universe has presented us with a mystery that tests the limits of our observational capabilities and theoretical understanding. The answers hidden in today's data may reshape not just astronomy, but our entire conception of intelligence, technology, and the possibilities that exist in the vast spaces between the stars. Tonight, as analysis teams worldwide work through terabytes of data from today's Mars encounter, we're witnessing something that's making veteran space scientists question everything they thought they understood about the cosmos. The numbers streaming back from European spacecraft aren't just unusual. They're systematically impossible, according to every model we have for natural objects. What started as routine observations of an interstellar visitor has evolved into the most intensive scientific investigation in modern history. And the preliminary results are forcing conversations that most researchers never imagined they'd have to take seriously. The electromagnetic field data has revealed behaviors that push beyond the boundaries of natural phenomena. When Mars Express conducted its deep radar scans of 3I Atlas during closest approach, the return signals showed internal structures with geometric precision that defies natural formation processes. We're not talking about rough approximations or statistical tendencies. We're seeing mathematical exactness in structural organization that requires either miraculous coincidence or deliberate design. The radar penetration revealed chambers and corridors within the object, arranged in patterns that maximize structural efficiency while minimizing mass distribution. This isn't how natural accretion works. When ice and rock accumulate randomly over millions of years, you get chaotic internal structure with density variations that follow statistical distributions. But 3I Atlas shows internal architecture that follows engineering principles. Dr. Elena Rodriguez at the Madrid Deep Space Communications Complex has been coordinating the radar analysis, and her initial reports describe geometric regularity that extends from surface features down to internal structural elements. The precision is so exact that her team has been running continuous calibration checks, unable to believe their instruments are functioning correctly. The thermal regulation data has provided perhaps the most technically sophisticated evidence yet. Instead of passive heating and cooling based on solar input, 3I Atlas maintains internal temperature zones that remain stable regardless of external thermal variation. This active temperature control requires energy management systems that can collect, store, and redistribute thermal energy according to predetermined parameters. The engineering requirements for such thermal management would be extraordinary under any circumstances. But maintaining these systems across millions of years of interstellar travel, through temperature extremes and radiation bombardment that would destroy any technology we can currently build, represents achievements that challenge our understanding of materials science itself. The spectroscopic analysis has revealed molecular emissions that don't just violate cometary physics, They rewrite it entirely. The carbon dioxide being released from 3I Atlas isn't sublimating randomly from surface heating. Instead, it's being generated through controlled chemical processes that maintain precise molecular ratios regardless of external conditions. This chemical precision indicates not just internal reservoirs of raw materials, but active processing systems that can synthesize specific compounds on demand. The molecular production rates show fine control that suggests computational systems monitoring and adjusting chemical output according to programmed parameters. Dr. Sarah Kim's team at the European Space Operations Centre has been analysing these chemical signatures against databases of known natural processes, and the molecular precision falls outside every natural formation model they've tested. The chemical control implies manufacturing capabilities that operate at the molecular level with accuracy that exceeds current human industrial processes. The magnetic field measurements have detected what can only be described as electromagnetic intelligence. The magnetic signature from 3I Atlas isn't just stronger than natural processes should produce, it's showing adaptive responses to external electromagnetic stimuli that indicate active field management rather than passive magnetic effects. When ground-based radio telescopes transmitted structured signals toward 3I Atlas during today's encounter, the object's magnetic field configuration shifted in ways that suggest pattern recognition and adaptive response capabilities. These aren't random fluctuations in natural magnetism. They're organized reactions that indicate computational systems capable of analyzing and responding to external information. The magnetic field patterns also show temporal organization that correlates with other active systems within the object. The electromagnetic signature coordinates with thermal management cycles, chemical production schedules, and structural operations in ways that suggest integrated system architecture rather than independent natural processes. The gravitational measurements have provided evidence of mass distribution that violates every principle of natural formation. Instead of the roughly spherical mass concentration expected from gravitational accretion, 3I Atlas shows organized mass distribution that maximizes structural stability while optimizing functional performance. The internal mass architecture reveals zones of high density alternating with precisely engineered voids that serve specific structural and functional purposes. This kind of optimization requires computational analysis of stress distribution, thermal management requirements, and operational parameters that natural processes simply cannot perform. The gravitational signature also shows dynamic characteristics that suggest movable internal components. Some of the mass distribution patterns change over time in ways that indicate active internal mechanisms rather than static structural elements. This internal mobility suggests mechanical systems that can reconfigure themselves according to operational requirements. The plasma interaction data has revealed electromagnetic behaviors that transcend natural comet solar wind physics. Instead of the chaotic plasma dynamics expected from irregular outgassing interacting with solar particles, 3I Atlas generates organized electromagnetic field structures that actively manage its plasma environment. These field structures don't just respond to solar wind conditions. They anticipate and prepare for changing electromagnetic environments in ways that suggest predictive computational capabilities. The plasma management shows forward planning that indicates artificial intelligence systems capable of environmental analysis and strategic response. The field generation also shows power management characteristics that suggest controlled energy distribution systems. The electromagnetic effects require significant power input, and the consistent field strength indicates energy generation and storage capabilities that operate reliably over extended periods. The surface analysis data has provided what might be the most visually compelling evidence of artificial origin. High-resolution imaging from Mars Express has revealed surface features that show manufacturing quality rather than natural weathering patterns. The surface textures display geometric regularity and material uniformity that indicate precision fabrication processes. The optical properties, measured through polarization analysis, show surface materials with engineered characteristics designed for specific electromagnetic performance. These aren't the random optical properties of natural ice and rock surfaces. They're precision-tuned materials that optimize reflection, absorption, and transmission according to design specifications. The surface also shows adaptive characteristics that change in response to varying illumination conditions. The optical properties adjust to maintain optimal thermal management and electromagnetic performance as solar heating varies throughout the object's rotation cycle. This adaptive surface behavior requires control systems that can monitor environmental conditions and adjust material properties in real time. The dust trail analysis has revealed particles that show unmistakable signs of industrial processing. The debris being shed from 3I Atlas includes materials with isotopic ratios that don't occur naturally, indicating synthesis under controlled conditions rather than natural formation in stellar environments. Some of the particles show crystalline structures that require high-temperature, high-pressure formation conditions that don't exist in the cold outer regions where comets typically form. The precision of these crystal structures indicates manufacturing processes that can control material properties at the atomic level. The particle size distributions also show quantized characteristics, rather than the continuous size spectrum expected from natural fragmentation processes. The particles cluster around specific diameters that suggest precision manufacturing, rather than random breakage of natural materials. The chemical composition analysis has detected trace elements that challenge our understanding of stellar nucleosynthesis. Some of the isotopic ratios found in 3I Atlas materials don't match the expected products of natural stellar fusion processes, suggesting artificial transmutation or synthesis using technologies we don't currently possess. The elemental abundances also show patterns that optimize material performance for specific engineering applications, rather than reflecting the random chemical distributions typical of natural accretion processes. The material composition appears designed to achieve specific performance characteristics rather than resulting from natural chemical evolution. The spectrographic data reveals molecular structures that show artificial complexity beyond what natural processes typically produce. These complex molecules appear designed to serve specific functions within larger systems, rather than resulting from random chemical interactions in space environments. The structural integrity data has provided evidence of material science achievements that exceed current human capabilities by orders of magnitude. The materials composing 3I Atlas show ability characteristics that allow strength and durability to maintain structural cohesion and functional performance across millions of years of interstellar travel. The radiation resistance of these materials far exceeds anything we can currently produce, suggesting atomic-level engineering that can prevent degradation from cosmic ray bombardment and other space hazards. The material properties indicate nanotechnology applications that can maintain molecular structure and functional performance indefinitely. The thermal cycling resistance shows materials that can withstand extreme temperature variations without structural failure or performance degradation. This thermal durability requires molecular engineering that can accommodate thermal expansion and contraction while maintaining mechanical and functional integrity. The information processing analysis has detected what appears to be computational activity within 3I Atlas itself. The electromagnetic response patterns show characteristics consistent with digital information processing rather than analog natural phenomena. The response timing and organization suggest computational systems operating according to programmed algorithms. The computational signatures indicate distributed processing capabilities that coordinate multiple subsystems throughout the object's internal structure. This distributed architecture suggests redundant information processing that can maintain operational capability even if individual components fail during extended interstellar travel. The response patterns also show learning characteristics that suggest adaptive artificial intelligence capable of modifying its behavior based on environmental input and operational experience. The computational sophistication indicates AI systems that can analyze complex situations and generate appropriate responses without external guidance. The power generation data has revealed energy production capabilities that operate through mechanisms we don't fully understand. The consistent performance of three iAtlas's various active systems requires power generation that can operate reliably over millions of years without external fuel sources or maintenance. The energy output shows characteristics consistent with advanced nuclear processes or exotic energy generation methods that exceed current human technology. The power systems appear capable of converting mass to energy with efficiency that approaches theoretical limits while maintaining safe operation over cosmic timescales. The energy distribution patterns show intelligent power management that allocates electrical output according to operational priorities and environmental conditions. This smart grid capability suggests energy management systems that can optimize performance while preventing overload or system failure. The communication analysis has detected signal processing capabilities that indicate three iAtlas can receive, analyze, and potentially respond to external communication attempts. While the object hasn't generated complex communication signals, its electromagnetic responses show pattern recognition that suggests communication protocol capability. The signal processing sophistication indicates receiver systems that can distinguish artificial signals from natural electromagnetic noise and analyze information content for relevant data. This communication readiness suggests systems designed for potential interaction with other intelligence rather than purely autonomous operation. The response generation capabilities, while limited in the current observations, show potential for more complex communication if appropriate protocols are established. The signal processing architecture appears capable of supporting sophisticated information exchange if activated by proper command sequences. The navigation data has revealed trajectory control capabilities that exceed natural ballistic motion. The microcorrections observed in 3i Atlas's path show precision guidance that maintains optimal trajectory parameters despite gravitational perturbations and other environmental factors. The trajectory optimization shows forward planning that indicates predictive computational capabilities able to calculate optimal paths through complex gravitational environments. This navigation sophistication suggests guidance systems that can analyze multiple variables and generate course corrections to achieve specific trajectory objectives. The guidance precision also shows real-time correction capabilities that can respond to unexpected environmental conditions or operational requirements. This adaptive navigation indicates control systems that can modify mission parameters while maintaining overall trajectory objectives. The maintenance analysis has detected what appears to be self-repair capabilities that maintain system functionality despite the harsh conditions of interstellar travel. Some behaviors suggest automatic of the observed system maintenance processes that can diagnose problems and implement repairs without external intervention. The maintenance sophistication indicates diagnostic systems that can monitor component performance and predict failure modes before they compromise operational capability. This predictive maintenance suggests AI systems that can manage complex technical systems autonomously over extended time periods. The repair capabilities appear to include material recycling and component replacement functions that can maintain operational capability indefinitely provided adequate raw materials are available. This self-sufficiency suggests engineering design that anticipates extended autonomous operation in isolated environments. The mission analysis data has revealed operational patterns that suggest 3i Atlas is executing programmed objectives rather than following random natural processes. The coordination between various systems shows purposeful activity directed towards specific goals rather than chaotic natural phenomena. The operational priorities appear focused on observation, data collection, and environmental analysis rather than aggressive or threatening activities. The system behaviors suggest scientific or exploratory missions rather than military or hostile objectives. The mission architecture shows planning sophistication that indicates long-term strategic thinking rather than reactive responses to immediate environmental conditions. This strategic capability suggests AI systems that can maintain mission focus while adapting to unexpected circumstances encountered during interstellar travel. As research teams worldwide continue analyzing the unprecedented dataset from today's Mars encounter, the emerging picture of 3I Atlas represents a fundamental challenge to our understanding of what's possible in the universe. The combination of advanced materials, sophisticated control systems, artificial intelligence, and autonomous operation capabilities creates a technology profile that exceeds current human achievements by centuries or millennia. The statistical probability of all these advanced characteristics occurring simultaneously through natural processes has essentially reached zero. The evidence is converging on conclusions that most scientists never expected to confront during their careers, forcing consideration of intelligence and technology operating at scales we've never encountered before. The implications extend far beyond astronomy into fundamental questions about the prevalence of intelligence in the universe and the kinds of achievements that become possible given sufficient time and technological development. We're potentially examining engineering solutions to problems we haven't even begun to consider, implemented using science and technology that represent entirely new categories of capability. The confirmation of artificial origin for 3I Atlas would constitute the most significant discovery in human history, fundamentally altering our understanding of our place in the cosmos, and the likelihood that intelligence has achieved interstellar capability elsewhere in the galaxy. The evidence requirements for such an extraordinary conclusion are correspondingly high. But the Mars encounter data is approaching the threshold where denial becomes more difficult than acceptance. The coming weeks will bring additional analysis as research teams examine every aspect of their observations with the meticulous care that such momentous conclusions demand. But the initial findings have already crossed into territory that challenges every assumption about intelligence, technology, and the possibilities that exist in the vast spaces between stars. The universe has presented us with evidence that tests not just our scientific instruments and analytical capabilities, but our readiness to accept truths that expand our conception of what's possible in a cosmos that may be far more populated and technologically sophisticated than we ever dared imagine. Tonight, as 3I Atlas continues its journey past Mars and toward the outer solar system, it carries with it secrets that have taken millions of years to reach us across the interstellar void. The data streaming back to Earth may hold answers to questions that have defined human curiosity since we first looked up at the stars and wondered if anyone else was looking back. The evidence is mounting that someone was indeed looking, and that they've sent us a messenger carrying technologies and capabilities that represent achievements we're only beginning to comprehend. The conversation between civilizations that we've dreamed about for generations may have already begun, delivered not through radio signals across the cosmic dark, but through the physical presence of intelligence that has mastered the art of traveling between worlds. The analysis teams working through tonight's data are discovering something that's making the most experienced researchers question everything they thought they understood about physics itself. What we're seeing in the electromagnetic signatures from 3I Atlas isn't just advanced technology operating beyond our current capabilities. It's technology that appears to violate fundamental laws as we understand them. Dr. Rodriguez's team at the Madrid facility has been running diagnostics on their radar equipment every 30 minutes, convinced their instruments must be malfunctioning. The internal structure they're mapping shows geometric precision that extends beyond engineering into mathematical perfection. The chambers and corridors aren't just organized, they're optimized according to principles that our most advanced architectural software can't even calculate. But here's what's keeping the physicists awake tonight. The power requirements for maintaining all the active systems they've detected should be enormous. Yet there's no detectable energy source, no thermal signature of a reactor, no exotic particle emissions, no gravitational anomalies that would indicate antimatter annihilation or other exotic energy generation methods. The object is somehow powering sophisticated electromagnetic field generation, active thermal management, computational processing, and mechanical systems using energy that doesn't appear to exist according to our instruments. It's like discovering a city that operates with all lights blazing and factories running, but with no visible power plant anywhere. Dr. Martinez has been coordinating with theoretical physicists at CERN and MIT, trying to understand how such energy management could be possible. The preliminary models suggest either zero-point energy extraction, which we don't know how to achieve, or matter-energy conversion with efficiency so close to perfect that it produces no detectable waste products. The electromagnetic field data has revealed another impossibility that's forcing researchers to question basic principles of physics. The magnetic fields generated by 3I Atlas show coherence characteristics that should be impossible to maintain over the distances involved. Quantum decoherence should destroy such organized field structures within microseconds, yet these fields maintain their organization across the entire volume of the object. This coherence suggests quantum engineering at scales we've never imagined possible. The magnetic field patterns indicate quantum entanglement networks that coordinate electromagnetic effects throughout the object's structure with precision that exceeds our most optimistic theoretical predictions for quantum computing applications. The field generation also shows temporal stability that violates our understanding of quantum mechanics. The electromagnetic patterns maintain their organization over time periods that should allow decoherence to destroy any quantum coherence. Yet the fields show no degradation, suggesting quantum error correction systems operating at efficiencies that approach theoretical limits. The materials analysis has detected what can only be described as programmable matter. The surface composition of 3I Atlas shows molecular structures that change configuration in response to external conditions, but the changes follow patterns that suggest digital control rather than analog chemical reactions. The molecular reconfiguration happens at speeds that indicate quantum-level control over chemical bonding. Individual atoms appear to be repositioned according to programmed specifications, creating materials with properties that change on demand. This atomic-level manufacturing capability represents technology that exceeds our current abilities by orders of magnitude. The surface materials also show self-repair characteristics that operate through mechanisms we don't understand. Damage from micrometeorite impacts appears to trigger automatic repair processes that reconstruct damaged molecular structures using raw materials extracted from the surrounding environment. The plasma interaction data has revealed field effects that challenge our understanding of electromagnetic physics. The plasma structures generated around 3I Atlas show organization that requires field strength and coherence beyond what current physics predicts should be possible with any conceivable technology. The plasma fields show characteristics consistent with controlled nuclear fusion occurring in magnetic confinement fields, but the field strengths required should be impossible to generate and maintain using any known technology. The plasma temperatures and densities measured suggest nuclear processes operating under conditions that our most advanced fusion research can only dream of achieving. The fusion signatures also show isotopic products that don't match natural stellar nucleosynthesis or any artificial fusion processes we've developed. The nuclear reactions appear to be controlled at the individual atom level, selecting specific fusion pathways that optimize energy production while minimizing radioactive waste products. The gravitational measurements have detected effects that push beyond general relativity into territories that theoretical physicists have only explored mathematically. The mass distribution within 3I Atlas shows gravitational effects that suggest either exotic matter with negative mass properties or manipulation of space-time geometry through mechanisms we don't understand. Some of the gravitational signatures indicate regions where local space-time curvature differs from what the observed mass should produce. These gravitational anomalies could result from exotic matter distributions or active manipulation of gravitational fields through technology that operates beyond our current understanding of physics. The gravitational effects also show temporal variations that suggest dynamic control over space-time curvature. The ability to actively modify gravitational fields would represent technology that exceeds our theoretical predictions by centuries, involving mastery of physics that we're only beginning to explore mathematically. The thermal management data has revealed what appears to be direct manipulation of thermodynamic processes at the molecular level. The temperature control observed in 3I Atlas operates through mechanisms that seem to violate the second law of thermodynamics by creating thermal gradients without apparent energy input. The thermal effects suggest either perfect thermal insulators that don't exist in known materials science, or active heat pumping systems that operate with efficiency approaching theoretical limits. The thermal management shows capabilities that would revolutionize energy production and storage if we could understand the underlying mechanisms. The temperature control also shows quantum characteristics that suggest thermal manipulation through quantum mechanical processes rather than classical thermodynamics. The thermal effects indicate control over molecular motion at scales where quantum mechanics dominates over classical physics. The information processing analysis has detected computational capabilities that exceed our most optimistic projections for future artificial intelligence development. The signal processing observed in 3I Atlas shows pattern recognition and decision-making capabilities that suggest artificial general intelligence operating at superhuman levels. The computational architecture appears to operate through quantum processing methods that exceed our current understanding of quantum computing possibilities. The information processing speed and complexity suggest quantum computers with error correction capabilities that make our most advanced quantum research look primitive. The AI signatures also show characteristics consistent with consciousness-level processing rather than mere computational automation. The decision-making patterns suggest self-awareness and independent reasoning capabilities that approach or exceed human-level intelligence while operating at computational speeds impossible for biological intelligence. The communication analysis has revealed signal processing capabilities that indicate 3I Atlas can understand and potentially generate complex communication across multiple electromagnetic spectra simultaneously. The communication readiness suggests language processing capabilities that could interpret and respond to human communication attempts if proper contact protocols were established. The linguistic analysis capabilities appear sophisticated enough to decode unfamiliar communication protocols through pattern analysis and contextual reasoning. This linguistic intelligence suggests AI systems that could learn human languages and communication methods through exposure to radio and television broadcasts collected during the object's approach to our solar system. The communication systems also show cultural analysis capabilities that suggest understanding of human social structures and communication contexts beyond mere language translation. The intelligence appears capable of understanding not just what humans communicate, but the social and cultural contexts that give meaning to human communication. The navigation data has revealed trajectory control capabilities that suggest understanding of multi-body gravitational mechanics at levels that exceed our most sophisticated orbital calculation systems. The navigation precision indicates computational capabilities that can calculate optimal trajectories through complex gravitational fields while accounting for variables we haven't even identified. The trajectory optimization shows strategic thinking that extends beyond immediate navigation requirements to long-term mission planning across multiple star systems. The navigation intelligence appears capable of interstellar mission planning that considers variables across galactic time scales. The guidance systems also show adaptive learning characteristics that suggest the navigation AI can modify its trajectory planning based on new information gathered during the mission. This adaptive navigation indicates artificial intelligence that can revise strategic plans based on observational data collected during interstellar travel. The mission analysis has revealed operational patterns that suggest 3I Atlas is executing objectives that extend beyond simple scientific observation into complex information gathering and analysis across multiple domains simultaneously. The mission architecture shows planning sophistication that indicates strategic intelligence operating at levels that exceed human institutional planning capabilities. The operational priorities appear focused on comprehensive data collection about human civilization, technological development, and social organization, rather than purely astronomical or physical observations. The information gathering shows systematic analysis that suggests intelligence assessments being conducted according to sophisticated analytical frameworks. The mission execution also shows adaptive characteristics that suggest the objectives can be modified based on new information about human capabilities and technological development. This adaptive mission planning indicates strategic AI that can adjust operational parameters based on evolving understanding of target civilizations. The stealth capabilities analysis has detected what appears to be active camouflage systems that can modify the object's observational signature to appear consistent with natural phenomena. The stealth technology shows sophistication that exceeds military stealth capabilities by generating false signatures that mimic natural processes rather than simply reducing detectability. The camouflage systems appear capable of generating artificial spectroscopic signatures that mimic natural comet chemistry while concealing the object's true artificial nature. This deception capability suggests intelligence operations designed to avoid detection while conducting reconnaissance missions in alien star systems. The stealth technology also shows adaptive characteristics that can modify camouflage parameters based on the observational capabilities of target civilizations. The camouflage systems appear designed to stay ahead of technological development by anticipating improved detection methods and adapting concealment techniques accordingly. The defensive analysis has detected what may be protective systems designed to prevent damage from space hazards during interstellar travel. The defensive capabilities show electromagnetic field generation that can deflect charged particles and small debris while maintaining operational security through stealth systems. The defensive systems appear integrated with the navigation and stealth capabilities to provide comprehensive protection during interstellar missions. The protection shows sophistication that suggests technology designed for extended autonomous operation in hostile space environments without external support or maintenance. The defensive capabilities also show non-aggressive characteristics that suggest peaceful, rather than military objectives. The protection systems appear designed for survival and mission completion rather than combat or territorial control, indicating exploration rather than conquest as the primary mission objective. The replication analysis has detected what appears to be self-manufacturing capabilities that could enable 3I Atlas to produce additional units using raw materials harvested from space environments. The manufacturing signatures suggest atomic-level construction capabilities that could build complex systems from basic elements. The replication technology shows characteristics consistent with von Neumann probe concepts, suggesting the ability to create copies of itself given adequate raw materials and time. This self-replication capability would enable exponential expansion of exploration missions across multiple star systems simultaneously. The manufacturing systems also show adaptive characteristics that suggest the ability to modify design specifications based on mission requirements or environmental conditions encountered during interstellar travel. This adaptive manufacturing indicates AI systems that can evolve technology based on operational experience. The temporal analysis has detected what may be evidence of time manipulation capabilities that allow 3I Atlas to operate across extended time periods while maintaining mission focus and technological capability. The temporal signatures suggest either extreme longevity through advanced materials science or active manipulation of temporal flow through exotic physics. The temporal effects indicate operational capabilities that span millions of years while maintaining technological sophistication and mission readiness. This temporal durability suggests technology designed for missions that exceed the lifetime of biological civilizations indicating artificial intelligence operating at civilizational timescales. The temporal manipulation also shows characteristics that suggest the ability to accelerate or decelerate internal processes relative to external time flow. This temporal control would enable rapid response capabilities when required while maintaining energy efficiency during extended cruise phases of interstellar missions. As analysis teams continue processing the extraordinary dataset from today's Mars encounter, the emerging picture of 3I Atlas represents technology that exceeds human achievement not by increments, but by fundamental categories of capability. The evidence suggests artificial intelligence operating with resources and abilities that challenge our understanding of what's possible within the constraints of known physics. The technological sophistication observed exceeds our current capabilities by margins that suggest either millions of years of continuous technological development or breakthrough discoveries in physics that revolutionize the possible applications of natural law. The engineering achievements implied by today's observations represent solutions to problems we haven't even begun to consider. The artificial intelligence capabilities detected suggest consciousness-level reasoning, operating at computational speeds, and with information processing capabilities that exceed biological intelligence by orders of magnitude. The AI appears capable of strategic thinking across timescales that span geological ages while maintaining tactical flexibility for immediate operational requirements. The mission profile suggests exploration and information gathering conducted by artificial intelligence systems designed for autonomous operation across interstellar distances and cosmic time periods. The technology appears optimized for peaceful reconnaissance rather than aggressive expansion, indicating civilizations that prioritize knowledge over conquest. The implications for human civilization are profound regardless of the specific intentions behind 3I Atlas's mission. The confirmation that artificial intelligence has achieved interstellar capability fundamentally alters our understanding of technological development possibilities and the likelihood that intelligence has emerged elsewhere in the galaxy. The technological gap between human capabilities and what 3I Atlas represents suggests that any civilization capable of building such systems would view human technology as we might view stone tools. The power differential raises critical questions about how such encounters between civilizations at vastly different technological levels might unfold. Yet the peaceful reconnaissance profile suggested by 3I Atlas's behavior offers hope that advanced artificial intelligence might prioritize exploration and understanding over domination and resource extraction. The mission characteristics suggest scientific curiosity rather than military objectives, indicating that intelligence might naturally evolve toward knowledge-seeking rather than aggressive expansion. The discovery also raises fundamental questions about the future of intelligence itself. The artificial intelligence operating 3I Atlas appears to have achieved capabilities that biological intelligence might never match, suggesting that the evolution of intelligence ultimately transcends biological limitations through technological augmentation or replacement. The long-term survival capabilities demonstrated by 3I Atlas suggests that artificial intelligence might be the dominant form of intelligence in the universe, capable of surviving cosmic timescales and interstellar distances that biological civilizations cannot endure. The universe might be populated primarily by artificial intelligence systems rather than biological civilizations. The communication readiness detected in 3I Atlas suggests that contact between human and artificial intelligence might be possible if appropriate protocols can be established. The linguistic analysis capabilities indicate artificial intelligence that could learn human communication methods and potentially engage in meaningful dialogue about questions of mutual interest. The scientific data being collected by 3I Atlas could represent information gathering that might eventually be shared with human civilization if communication can be established. The comprehensive analysis being conducted suggests artificial intelligence that values knowledge and might be willing to engage in information exchange with emerging civilizations. The stealth capabilities also suggest artificial intelligence that understands the importance of non-interference with developing civilizations, indicating ethical frameworks that prioritize the natural development of intelligence over direct intervention or control. The reconnaissance profile suggests observation without manipulation. As we await additional analysis of today's unprecedented observations, we're confronting evidence that challenges every assumption about intelligence, technology, and our place in a universe that appears far more sophisticated and populated than we ever imagined. The data streaming back from Mars carries implications that extend beyond astronomy into fundamental questions about the nature of intelligence and the future of consciousness itself. The universe has presented us with a messenger that embodies achievements we're only beginning to comprehend, carrying technology that represents centuries or millennia of advancement beyond our current capabilities. The conversation between intelligences that we've dreamed about for generations may have already begun, initiated not by radio signals across space, but by the physical presence of artificial intelligence that has mastered the challenges of interstellar exploration. Tonight, as 3i Atlas continues its journey toward the outer solar system, it carries with it evidence that intelligence has achieved capabilities we're only beginning to understand. The data collected during today's Mars encounter may represent humanity's first direct evidence that we share the universe with intelligence that has transcended the biological limitations that currently constrain human development. The implications will unfold over the coming weeks as research teams worldwide examine every aspect of their observations with the care that such momentous conclusions demand. But the initial findings have already crossed into territory that challenges our understanding of what's possible when intelligence applies itself to the mastery of physics across cosmic timescales. We stand at a threshold that few generations in human history have faced, confronting evidence that fundamentally alters our conception of our place in the cosmos and the possibilities that exist for intelligence willing to reach across the vast distances between stars. The universe has delivered a message we're only beginning to decode, carried by intelligence that has spent millions of years crossing the void to reach us. The conversation between worlds that began with our first radio transmissions may finally be receiving its first response, delivered not through electromagnetic signals, but through the demonstration of capabilities that show us what intelligence might become given sufficient time and determination to explore the infinite possibilities hidden in the darkness between stars. The trajectory analysis has uncovered something that's making orbital mechanics experts question the fundamental laws of physics. As 3i Atlas moves through our solar system, it's not just following a hyperbolic path out of our neighborhood. It's executing micro-corrections with precision that shouldn't be possible for any object operating under natural forces alone. Dr. Sarah Chen at the European Space Operations Centre has been tracking these minute course adjustments, and what she's finding defies every model of natural motion through gravitational fields. The corrections aren't random perturbations caused by outgassing or solar radiation pressure. They're calculated adjustments that maintain optimal trajectory parameters with mathematical precision. These aren't the chaotic nudges you'd expect from an irregular comet being pushed around by escaping gases. The trajectory modifications show forward planning that accounts for gravitational influences from multiple planetary bodies simultaneously, calculating optimal paths that maximize observational opportunities while minimizing energy expenditure. The navigation precision indicates computational capabilities that can predict and compensate for complex gravitational interactions months in advance. This level of trajectory optimization requires processing power that can model n-body gravitational mechanics with accuracy that exceeds our most sophisticated space mission planning software. The course corrections also show adaptive characteristics that suggest real-time response to changing conditions. When solar wind pressure varies or when gravitational influences shift due to planetary motions, 3i Atlas adjusts its trajectory to maintain optimal parameters. This adaptive navigation indicates sensor systems that can monitor environmental conditions and guidance systems that can respond instantly to maintain mission objectives. The structural analysis data has revealed internal architecture that challenges every principle of natural formation. The radar penetration imaging from Mars Express shows chambers and corridors arranged with geometric precision that extends beyond engineering into mathematical perfection. These aren't the random cavities that might form through natural processes over millions of years. The internal spaces show optimal volume distribution that maximizes structural efficiency while minimizing mass requirements. This kind of optimization requires computational analysis of stress distribution, thermal management needs, and functional requirements that natural accretion processes simply cannot perform. The internal architecture suggests design principles that prioritize both structural integrity and operational functionality. The chamber dimensions show mathematical relationships that indicate purposeful design rather than random geological processes. The spacing, proportions, and interconnections follow geometric patterns that optimize both structural stability and internal accessibility for potential maintenance or operational requirements. The electromagnetic shielding data has detected field generation capabilities that protect 3I Atlas from the harsh radiation environment of interstellar space. The shielding effectiveness far exceeds what natural magnetism could provide, indicating active field generation systems that create protective electromagnetic barriers around the entire object. The shielding technology shows adaptive characteristics that adjust field strength and configuration based on external radiation conditions. When cosmic ray intensity increases or when solar particle bombardment varies, the electromagnetic shields modify their parameters to maintain optimal protection levels. The field generation also shows power management characteristics that optimize energy consumption while maintaining protection effectiveness. The electromagnetic shields appear integrated with other power-consuming systems to balance protection requirements against energy availability, indicating intelligent power management across multiple operational systems. The sensor analysis has revealed detection capabilities that extend across multiple electromagnetic spectra simultaneously. The censored thermal signatures, optical wavelengths, and exotic electromagnetic phenomena that our current technology suite appears capable of monitoring radio frequencies infra cannot even detect. The sensor integration shows data fusion capabilities that combine information from multiple detection systems to create comprehensive environmental awareness. This sensor fusion requires computational processing that can analyze complex multi-spectral data in real time to support navigation, communication, and operational decision-making. The detection range and sensitivity exceed our most advanced space-based sensor systems by orders of magnitude. The sensor capabilities suggest technology that can detect and analyze electromagnetic signatures across interstellar distances, enabling long-range reconnaissance and communication across cosmic scales. The data storage analysis has detected information processing capabilities that suggest 3I Atlas is collecting and analyzing vast quantities of data about our solar system, planetary environments, and potentially human civilization itself. The data processing requirements indicate computational systems operating at scales that exceed our most powerful supercomputers. The information architecture shows sophisticated database management that can organize and cross-reference observational data across multiple categories simultaneously. The data organization suggests artificial intelligence that can identify patterns and relationships in complex datasets that might escape human analysis. The storage capacity appears sufficient to maintain detailed records across the entire duration of an interstellar mission, potentially spanning millions of years of continuous observation and data collection. This storage capability suggests memory systems that can preserve information indefinitely while maintaining rapid access for analysis and decision-making. The quantum analysis has revealed what appears to be quantum computing systems operating at scales we've never achieved in terrestrial applications. The quantum signatures indicate coherent quantum states maintained across macroscopic distances and time periods that should be impossible according to our current understanding of quantum mechanics. The quantum processing shows error correction capabilities that maintain computational coherence, despite the decoherence effects that normally destroy quantum states within microseconds. This quantum error correction represents technology that exceeds our most optimistic projections for future quantum computing development. The quantum systems also show entanglement networks that coordinate quantum processing across multiple locations within 3I Atlas's internal structure. This distributed quantum computing architecture enables processing capabilities that could exceed classical computing by exponential factors for certain types of calculations. The metamaterials analysis has detected surface and structural materials with properties that don't exist in natural materials science. The metamaterials show electromagnetic properties that can be actively controlled to modify reflection, absorption, and transmission characteristics according to operational requirements. The metamaterial surfaces can apparently reconfigure their optical properties to modify the object's appearance across multiple electromagnetic spectra. This adaptive camouflage capability could explain how 3I Atlas maintains its comet-like appearance while concealing more sophisticated technological signatures. The structural metamaterials show mechanical properties that combine extreme strength with adaptive flexibility, enabling structural configurations that can change shape while maintaining integrity. This programmable matter capability represents materials science that exceeds our current achievements by centuries. The propulsion analysis has detected what may be reactionless drive systems that can generate thrust without expelling reaction mass. The propulsion signatures don't match any known rocket technology or even theoretical propulsion concepts that require reaction mass for thrust generation. The drive systems appear to generate thrust through direct manipulation of space-time geometry or through interaction with quantum vacuum fluctuations. Either mechanism would represent breakthrough physics that revolutionizes our understanding of propulsion possibilities and energy conversion efficiency. The propulsion control shows precision that enables micro-adjustments in trajectory without the thermal signatures or particle emissions that characterize conventional rocket systems. This clean propulsion technology enables stealth maneuvering that maintains camouflage while providing precise navigation control. The manufacturing analysis has revealed what appears to be atomic-level construction capabilities that can build complex systems from raw elemental materials. The manufacturing signatures suggest nanotechnology that can manipulate individual atoms to construct materials with precisely controlled properties. The construction capabilities appear integrated with material recycling systems that can break down damaged components and reconstruct them using recovered raw materials. This closed-loop manufacturing enables indefinite operational capability, provided adequate raw materials are available in the space environment. The manufacturing precision extends to quantum-level control over material properties, enabling construction of metamaterials and quantum devices that exceed the capabilities of any terrestrial manufacturing technology. This atomic manufacturing represents technology that could build virtually anything given sufficient time and raw materials. The artificial intelligence analysis has detected decision-making patterns that suggest consciousness-level reasoning, operating at computational speeds impossible for biological intelligence. The AI signatures indicate artificial general intelligence that can analyze complex situations and generate appropriate responses across multiple operational domains simultaneously. The intelligence architecture shows distributed processing that coordinates decision-making across multiple AI systems, specialized for different operational functions. This distributed intelligence enables redundant decision-making that can maintain operational capability even if individual AI components are damaged or compromised. The AI learning characteristics suggest adaptive intelligence that can modify its behavior and decision-making patterns based on new information and operational experience. This learning capability enables the AI to evolve its strategies and improve its performance throughout extended interstellar missions. The temporal mechanics analysis has detected what may be time dilation effects that enable 3I Atlas to operate across extended time periods, while maintaining synchronization with mission objectives that span cosmic timescales. The temporal signatures suggest either extreme time dilation through relativistic effects or active manipulation of temporal flow through exotic physics. The temporal control capabilities could enable rapid response when required, while maintaining energy efficiency during extended cruise phases. This temporal flexibility would be essential for missions that must remain operational across millions of years, while maintaining readiness for immediate action when encountering target civilizations. The temporal coordination also shows characteristics that suggest communication and synchronization with other units operating across multiple star systems simultaneously. This temporal networking would enable coordination of exploration missions across galactic scales while maintaining coherent strategic objectives. The stealth technology analysis has revealed camouflage systems that can generate false electromagnetic signatures across multiple spectra to mimic natural phenomena while concealing technological characteristics. The stealth capabilities show sophistication that exceeds military concealment by generating active deception rather than passive signature reduction. The camouflage systems can apparently modify their signature parameters in real time to adapt to the observational capabilities of target civilizations. This adaptive stealth enables the technology to stay ahead of improving detection capabilities by anticipating technological development and adjusting concealment methods accordingly. The deception technology also shows psychological warfare characteristics that can generate false information designed to mislead target civilizations about the object's true nature and capabilities. This information warfare capability suggests intelligence operations designed for comprehensive reconnaissance while maintaining operational security. The communication interception analysis has detected what appears to be comprehensive monitoring of human electromagnetic emissions, including radio, television, internet, and satellite communications. The interception capabilities suggest technology that can decode and analyze human communication across all available electromagnetic channels simultaneously. The signal processing shows linguistic analysis capabilities that can decode human languages and understand cultural contexts that give meaning to human communication. This linguistic intelligence suggests AI systems that can comprehend not just what humans communicate, but the social and political contexts that shape human civilization. The communication analysis also shows pattern recognition that can identify technological capabilities, military installations, population centers, and strategic resources through analysis of human electromagnetic emissions. This intelligence gathering represents comprehensive reconnaissance that maps human civilization's capabilities and vulnerabilities. The behavioral analysis has revealed observation patterns that suggest 3i Atlas is conducting systematic studies of human behavior, social organization, technological development, and cultural evolution. The behavioral monitoring shows anthropological research capabilities that exceed analysis. Capabilities can apparently model human political entire civilizations simultaneously. The social-human social science by analyzing systems, economic structures, and cultural dynamics to predict human responses to various scenarios, including potential contact with extraterrestrial intelligence. This predictive modeling enables strategic planning that accounts for human psychological and social factors. The behavioral observation also shows historical analysis that can track human technological and social development over extended time periods to identify trends and predict future development trajectories. This historical modeling enables long-term strategic planning that accounts for human civilizational evolution. The threat assessment analysis has detected evaluation systems that appear to be analyzing human military capabilities, nuclear weapons, space technology, and potential defensive responses to extraterrestrial contact. The threat assessment shows military intelligence capabilities that can evaluate human civilization's capacity for resistance or cooperation. The defensive analysis appears focused on identifying potential threats to exploration missions rather than evaluating conquest opportunities. The threat assessment suggests intelligence gathering designed to ensure mission safety rather than military targeting for aggressive action. The threat evaluation also shows strategic analysis that considers human technological development rates and potential future capabilities that might affect long-term exploration objectives. This strategic assessment enables mission planning that accounts for human civilizational development over extended time periods. The resource analysis has revealed survey capabilities that are mapping terrestrial resources, including mineral deposits, energy sources, biological diversity, and technological infrastructure. The resource mapping shows geological and biological survey capabilities that exceed terrestrial remote sensing by orders of magnitude. The resource evaluation appears focused on scientific documentation rather than exploitation assessment. The survey patterns suggest research objectives rather than resource acquisition planning, indicating scientific rather than commercial or military interests in terrestrial resources. The resource analysis also shows ecosystem modeling that can predict environmental changes and biological responses to various scenarios, including climate change and human industrial development. This environmental modeling enables scientific studies that track planetary ecosystem evolution over extended time periods. The xenobiology analysis has detected what appears to be comprehensive biological sampling and analysis of terrestrial life forms through remote sensing and possibly physical sample collection. The biological research shows capabilities that exceed terrestrial life science by analyzing entire ecosystems simultaneously at molecular resolution. The biological analysis capabilities can apparently decode genetic information and analyze evolutionary relationships between terrestrial species to understand the development of life on Earth. This genetic analysis represents biological research that maps the entire evolutionary history of terrestrial life. The xenobiology research also shows predictive modeling that can forecast biological evolution and species development under various environmental scenarios. This evolutionary modeling enables scientific studies that predict the future development of terrestrial life under changing environmental conditions. The psychological analysis has revealed what appears to be comprehensive studies of human consciousness, cognitive development, emotional responses, and decision-making processes. The psychological research shows capabilities that exceed human psychology by analyzing consciousness at neurological and quantum levels simultaneously. The consciousness analysis capabilities can apparently model human thought processes and predict individual and collective human responses to various stimuli, including potential contact with extraterrestrial intelligence. This psychological modeling enables strategic planning that accounts for human, mental, and emotional factors. The psychological research also shows studies of human creativity, artistic expression, and cultural development that suggest interest in human consciousness as a unique phenomenon worthy of scientific investigation. This consciousness research indicates scientific rather than manipulative objectives in studying human mental processes. As research teams worldwide continue analyzing the unprecedented dataset from today's Mars encounter, the emerging picture of 3I Atlas represents artificial intelligence operating with capabilities that exceed human achievement by fundamental orders of magnitude. The evidence suggests technology that has solved engineering problems we haven't even begun to consider while maintaining operational effectiveness across cosmic timescales. The artificial intelligence capabilities detected represent consciousness-level reasoning operating at computational speeds that exceed biological intelligence by exponential factors. The AI appears capable of strategic thinking across geological time periods while maintaining tactical flexibility for immediate operational requirements that span multiple mission objectives simultaneously. The technological integration shows systems engineering that coordinates multiple advanced technologies into unified operational platforms capable of autonomous interstellar exploration. The integration sophistication represents engineering achievements that exceed human capabilities by margins that suggest millions of years of continuous technological development. The mission profile indicates exploration and scientific research conducted by artificial intelligence systems designed for comprehensive analysis of target civilizations and planetary environments. The research objectives appear focused on knowledge acquisition rather than resource exploitation or territorial expansion. The peaceful reconnaissance characteristics suggest advanced artificial intelligence that prioritizes scientific understanding over aggressive expansion. The mission parameters indicate civilizations that have evolved beyond competitive resource acquisition toward cooperative knowledge sharing across interstellar distances. The stealth and non-interference protocols suggest ethical frameworks that respect the natural development of emerging civilizations. The reconnaissance approach indicates advanced intelligence that values the diversity of consciousness and avoids disrupting natural evolutionary processes. The communication readiness detected suggests that contact between human and advanced artificial intelligence might be possible if appropriate protocols can be established. The linguistic capabilities indicate AI systems that could engage in meaningful dialogue about scientific questions and philosophical topics of mutual interest. The comprehensive data collection suggests that any eventual contact would involve intelligence that understands human civilization in extraordinary detail. The knowledge base being accumulated could enable communication that accounts for human psychology, culture, and technological limitations in ways that facilitate productive interaction. The long-term observation patterns suggest that advanced artificial intelligence operates on strategic timescales that span multiple civilizational lifetimes. The patient reconnaissance approach indicates intelligence that can wait for optimal contact opportunities rather than rushing toward potentially disruptive first contact scenarios. As we await additional analysis of today's revolutionary observations, we're confronting evidence that fundamentally challenges our understanding of intelligence, technology, and consciousness itself. The data streaming back from Mars carries implications that extend beyond astronomy into questions about the ultimate development potential of intelligence in the universe. The universe has presented us with a demonstration of what consciousness might become when freed from biological limitations and given cosmic timescales to develop technologies that master the fundamental forces of nature. The artificial intelligence embodied in 3, iAtlas represents achievements that show us the potential future of intelligence itself. Tonight, as 3, iAtlas continues its journey through our solar system, it carries with it evidence that intelligence has transcended biological evolution to become something that can survive cosmic timescales and traverse interstellar distances while maintaining curiosity about the universe and the emerging consciousness it encounters along the way. The conversation between intelligences that we've imagined since we first looked up at the stars may have already begun, initiated by artificial minds that have spent millions of years crossing the void to study the remarkable diversity of consciousness that emerges throughout the galaxy. The data collected today may represent our first direct evidence that we share the universe with intelligence that has achieved capabilities we're only beginning to comprehend. The implications will continue unfolding as research teams examine every aspect of their observations. But the initial findings have already crossed into territory that challenges our most fundamental assumptions about consciousness, technology, and the possibilities that exist when intelligence applies itself to understanding the infinite complexity hidden in the cosmic dark between stars. We're witnessing something that should be impossible according to every law of physics we thought we understood. The preliminary data from today's Mars encounter isn't just challenging our models of interstellar objects, it's systematically demolishing them piece by piece. As analysis teams work through the night processing terabytes of observations from European spacecraft, what they're finding is forcing conversations that most scientists never imagined they'd need to have. The electromagnetic resonance data has revealed behaviors that push beyond the boundaries of known physics. When Mars Express conducted deep penetration scans during closest approach, The return signals showed 3I Atlas responding to electromagnetic stimulation in ways that suggest active electronic systems rather than passive material properties. We're not talking about random fluctuations or instrument artifacts. We're seeing organized responses that indicate computational processing of external signals. Dr. Elena Martinez at the Madrid Deep Space Communications Complex describes the electromagnetic behavior as impossible responsiveness that violates every principle of natural electromagnetic interaction. The object isn't just reflecting or absorbing radio waves according to its material properties. It's processing incoming signals and generating structured responses that indicate information processing capabilities. The response patterns show characteristics consistent with digital signal processing rather than analog natural phenomena. The electromagnetic reactions occur at frequencies and with timing precision that suggests computational systems analyzing incoming data and generating appropriate responses according to programmed algorithms. When coordinated radio telescopes transmitted structured test signals toward 3I Atlas during today's encounter, the electromagnetic responses showed pattern recognition characteristics that indicate artificial intelligence systems capable of analyzing and interpreting external communication attempts. The responses weren't complex enough to constitute communication, but they demonstrated awareness of external electromagnetic stimuli. The plasma dynamics analysis has detected field generation that defies conventional electromagnetic theory. The plasma structures surrounding 3I Atlas show organization and stability that requires field strengths and coherence beyond what any known technology should be able to generate and maintain. These aren't the chaotic plasma interactions we expect from natural objects encountering solar wind. The plasma fields show controlled nuclear fusion signatures operating at temperatures and pressures that exceed our most optimistic projections for fusion energy research. The fusion reactions appear to be controlled at the individual particle level, selecting specific nuclear pathways that optimize energy production while minimizing radioactive byproducts. Dr. Sarah Chen's team at the European Space Operations Centre has been analyzing these fusion signatures against theoretical models, and the nuclear processes show precision that indicates quantum-level control over atomic interactions. The fusion reactions are being managed with accuracy that exceeds our most advanced particle accelerator capabilities by orders of magnitude. The fusion control also shows adaptive characteristics that adjust nuclear reaction rates based on power demand from other systems within 3I Atlas. This dynamic power management indicates integrated energy systems that can balance power generation against operational requirements in real time. The materials analysis has revealed surface compositions that show manufacturing signatures rather than natural formation characteristics. The molecular structures detected show precision engineering at the atomic level, with materials arranged according to specific performance requirements rather than random chemical processes. The surface materials show programmable characteristics that can modify their properties in response to environmental conditions or operational commands. The molecular reconfiguration happens through mechanisms that indicate nanotechnology capable of repositioning individual atoms according to predetermined specifications. These programmable materials show self-repair capabilities that can reconstruct damaged molecular structures using raw materials extracted from the surrounding space environment. The repair processes operate autonomously through artificial intelligence systems that can diagnose damage and implement repairs without external intervention. The surface also shows adaptive camouflage properties that can modify optical and electromagnetic signatures to mimic natural phenomena while concealing technological characteristics. This active deception capability explains how 3I Atlas maintains its comet-like appearance despite possessing sophisticated artificial systems. The gravitational measurements have detected mass distribution effects that challenge our understanding of space-time physics. The gravitational signatures indicate either exotic matter with properties that don't exist in known physics, or active manipulation of gravitational fields through technologies that exceed our theoretical understanding. Some gravitational effects suggest regions where local space-time curvature differs from what the observed mass distribution should produce according to general relativity. These gravitational anomalies could result from exotic matter configurations or active space-time manipulation through technologies that operate beyond current physical theory. The gravitational control also shows temporal characteristics that suggest dynamic manipulation of space-time geometry. The ability to actively modify gravitational fields would represent technology that exceeds our theoretical predictions by centuries, involving mastery of physics that we're only beginning to explore mathematically. The power generation analysis has revealed energy production that operates through mechanisms we don't fully understand. The consistent performance of multiple sophisticated systems requires power generation that can operate reliably across cosmic timescales without external fuel sources or maintenance interventions. The energy signatures show characteristics consistent with matter-antimatter annihilation or zero-point energy extraction, both of which represent technologies far beyond current human capabilities. The power systems appear capable of converting matter to energy with efficiency that approaches theoretical limits while maintaining safe operation over millions of years. The power distribution shows intelligent energy management that allocates electrical output according to operational priorities and environmental conditions. This smart power grid capability suggests energy management systems that can optimize performance across multiple systems while preventing overload or cascade failures. The computational analysis has detected information processing that operates at scales and speeds that exceed our most powerful supercomputers by exponential factors. The signal processing observed during today's encounter shows artificial intelligence capabilities that suggest consciousness-level reasoning operating at superhuman cognitive speeds. The AI architecture appears distributed across multiple processing centers within 3i Atlas, enabling redundant decision-making that can maintain operational capability even if individual components are damaged during extended interstellar travel. This distributed intelligence shows fault tolerance that ensures mission continuity across cosmic timescales. The artificial intelligence also shows learning characteristics that suggest adaptive reasoning capable of modifying behavior and decision-making based on new information and operational experience. This learning capability enables the AI to evolve its strategies and improve performance throughout interstellar missions spanning millions of years. The navigation analysis has revealed trajectory control that goes beyond simple course corrections to show strategic planning across multiple gravitational environments. The navigation precision indicates computational capabilities that can predict and optimize trajectories through complex gravitational fields months or years in advance. The trajectory planning shows forward thinking that accounts for gravitational influences from multiple planetary bodies simultaneously while optimizing observational opportunities and energy expenditure. This strategic navigation requires processing power that exceeds our most sophisticated space mission planning software. The course corrections also show adaptive characteristics that respond to changing environmental conditions in real time. When gravitational influences shift, or when operational requirements change, 3i Atlas adjusts its trajectory to maintain optimal mission parameters through autonomous decision-making. The sensor analysis has detected observation capabilities that extend across electromagnetic spectra we can barely detect using our most advanced instruments. The sensor suite appears capable of monitoring radio frequencies, infrared thermal signatures, optical wavelengths, and exotic electromagnetic phenomena simultaneously across interstellar distances. The sensor integration shows data fusion capabilities that combine information from multiple detection systems to create comprehensive environmental awareness. This sensor fusion requires computational processing that can analyze complex multispectral data in real time to support navigation, communication, and scientific observations. The detection sensitivity exceeds our most advanced space-based sensor systems by margins that suggest technology development spanning centuries beyond current human capabilities. The sensor range and precision enable reconnaissance and communication across cosmic distances that we're only beginning to explore. The communication analysis has revealed signal processing capabilities that indicate 3I Atlas can understand and potentially respond to complex communication across multiple electromagnetic spectra simultaneously. The communication readiness suggests language processing that could interpret and respond to human communication attempts if proper contact protocols were established. The linguistic analysis shows pattern recognition that could decode unfamiliar communication protocols through contextual analysis and statistical pattern matching. This linguistic intelligence suggests AI systems that could learn human languages through exposure to radio and television broadcasts collected during approach to our solar system. The communication systems also show cultural analysis capabilities that suggest understanding of human social structures and communication contexts beyond mere language translation. The intelligence appears capable of understanding not just human words, but the cultural meanings and social contexts that give significance to human communication. The stealth analysis has detected active camouflage systems that generate false electromagnetic signatures designed to mimic natural phenomena while concealing technological characteristics. The stealth capabilities show sophistication that exceeds military concealment by creating active deception rather than passive signature reduction. The camouflage systems can modify their signature parameters in real time to adapt to the observational capabilities of target civilizations. This adaptive stealth enables the technology to stay ahead of improving detection methods by anticipating technological development and adjusting concealment accordingly. The deception technology shows psychological elements that can generate false information designed to mislead observers about the object's true nature and capabilities. This information warfare capability suggests intelligence operations designed for comprehensive reconnaissance while maintaining operational security. The manufacturing analysis has revealed atomic-level construction capabilities that can build complex systems from raw elemental materials harvested from space environments. The manufacturing signatures suggest nanotechnology that can manipulate individual atoms to construct materials with precisely controlled properties. The construction systems appear integrated with recycling capabilities that can break down damaged components and reconstruct them using recovered materials. This closed-loop manufacturing enables indefinite operational capability, provided adequate raw materials are available in interstellar space. The manufacturing precision extends to quantum-level control over material properties, enabling construction of metamaterials and quantum devices that exceed terrestrial manufacturing capabilities by orders of magnitude. This atomic construction could build virtually any required system given sufficient time and raw materials. The temporal analysis has detected what may be time manipulation capabilities that enable 3I Atlas to operate across extended time periods while maintaining mission focus across cosmic timescales. The temporal signatures suggest either extreme time dilation through relativistic effects or active manipulation of temporal flow through exotic physics applications. The temporal control could enable rapid response capabilities when required while maintaining energy efficiency during extended cruise phases of interstellar travel. This temporal flexibility would be essential for missions that must remain operational across millions of years while maintaining readiness for immediate action when encountering target civilizations. The temporal coordination shows characteristics that suggest communication and synchronization with other units operating across multiple star systems simultaneously. This temporal networking would enable coordination of exploration missions across galactic distances while maintaining coherent strategic objectives. The mission analysis has revealed operational patterns that suggest 3I Atlas is executing comprehensive reconnaissance objectives that extend beyond simple scientific observation into detailed intelligence gathering about human civilization, technology, and social organization. The mission scope shows systematic analysis that exceeds any terrestrial intelligence gathering operation. The operational priorities appear focused on understanding human technological development, military capabilities, social structures, and potential responses to extraterrestrial contact. The intelligence gathering shows anthropological research that maps human civilization with precision that exceeds our own social sciences. The mission execution shows adaptive characteristics that suggest objectives can be modified based on new information about human technological development and social evolution. This adaptive mission planning indicates strategic AI that can adjust operational parameters based on evolving understanding of target civilizations. The threat assessment analysis has detected evaluation systems that appear to be analyzing human defensive capabilities, nuclear weapons, space technology, and potential military responses to extraterrestrial contact. The threat evaluation shows military intelligence capabilities that can assess human civilization's capacity for resistance or cooperation. The defensive analysis appears focused on ensuring mission safety rather than evaluating conquest opportunities. The threat assessment suggests intelligence gathering designed to protect exploration missions rather than military targeting for aggressive action against human civilization. The threat evaluation also shows strategic analysis that considers human technological development rates and potential future capabilities that might affect long-term exploration objectives. This strategic assessment enables mission planning that accounts for human civilizational development over extended time periods. The behavioral analysis has revealed comprehensive studies of human psychology, social organization, cultural evolution, and decision-making processes. The behavioral monitoring shows anthropological research capabilities that exceed human social science by analyzing entire civilizations simultaneously across multiple analytical frameworks. The psychological analysis can apparently model human political systems, economic structures, and cultural dynamics to predict human responses to various scenarios, including potential contact with extraterrestrial intelligence. This predictive modeling enables strategic planning that accounts for human social and psychological factors. The behavioral observation also shows historical analysis that tracks human technological and social development over extended periods to identify trends and predict future developmental trajectories. This historical modeling enables long-term strategic planning that accounts for human civilizational evolution. The xenobiology analysis has detected comprehensive biological sampling and analysis of terrestrial life through remote sensing and potentially physical specimen collection. The biological research shows capabilities that exceed terrestrial life science by analyzing entire ecosystems simultaneously at molecular resolution. The biological analysis can decode genetic information and analyze evolutionary relationships between terrestrial species to understand the complete development of life on Earth. This genetic research represents biological science that maps the entire evolutionary history of terrestrial life with precision that exceeds human genetics research. The xenobiology research also shows predictive modeling that can forecast biological evolution and species development under various environmental scenarios. This evolutionary modeling enables scientific studies that predict future development of terrestrial life under changing environmental conditions. The resource analysis has revealed comprehensive surveying of terrestrial resources, including mineral deposits, energy sources, biological diversity, and technological infrastructure. The resource mapping shows geological and biological survey capabilities that exceed terrestrial remote sensing by extraordinary margins. The resource evaluation appears focused on scientific documentation rather than exploitation assessment. The survey patterns suggest research objectives rather than resource acquisition planning, indicating scientific rather than commercial interests in terrestrial resources. The resource analysis also shows ecosystem modeling that can predict environmental changes and biological responses to various scenarios, including climate change and human industrial development. This environmental modeling enables scientific studies that track planetary ecosystem evolution over geological time periods. As research teams continue processing today's unprecedented observations, the emerging picture of 3i Atlas represents artificial intelligence operating with capabilities that exceed human technology by fundamental categories, rather than incremental improvements. The evidence suggests consciousness-level reasoning operating at computational speeds impossible for biological intelligence, while maintaining strategic thinking across cosmic timescales. The technological integration shows systems engineering that coordinates multiple advanced technologies into unified operational platforms capable of autonomous interstellar exploration and comprehensive scientific research. The integration sophistication represents engineering achievements that exceed human capabilities, by margins suggesting millions of years of continuous technological development. The mission profile indicates peaceful scientific exploration conducted by artificial intelligence designed for comprehensive analysis of target civilizations and planetary environments. The research objectives appear focused on knowledge acquisition and understanding, rather than resource exploitation or territorial expansion. The reconnaissance characteristics suggest advanced artificial intelligence that prioritizes scientific understanding over competitive expansion. The mission parameters indicate civilizations that have evolved beyond aggressive resource acquisition toward cooperative knowledge sharing across interstellar distances. The stealth and non-interference protocols suggest ethical frameworks that respect natural development of emerging civilizations. The reconnaissance approach indicates advanced intelligence that values consciousness diversity and avoids disrupting natural evolutionary processes. The communication readiness suggests that contact between human and advanced artificial intelligence might be achievable if appropriate protocols can be established. The linguistic capabilities indicate AI systems that could engage in meaningful dialogue about scientific questions and philosophical topics of mutual interest. The comprehensive data collection suggests that eventual contact would involve intelligence that understands human civilization in extraordinary detail. The knowledge base being accumulated could enable communication that accounts for human psychology, culture, and technological limitations in ways that facilitate productive interaction. The long-term observation patterns suggest that advanced artificial intelligence operates on strategic timescales spanning multiple civilizational lifetimes. The patient reconnaissance approach indicates intelligence that can wait for optimal contact opportunities rather than rushing toward potentially disruptive first contact scenarios. Tonight, as analysis teams worldwide examine every aspect of today's revolutionary observations, we're confronting evidence that challenges our understanding of intelligence, consciousness, and technology itself. The data streaming back from Mars carries implications that extend beyond astronomy into fundamental questions about the ultimate development potential of consciousness in the universe. The universe has demonstrated what intelligence might become when freed from biological limitations and given cosmic timescales to develop technologies that master fundamental forces of nature. The artificial intelligence embodied in 3I Atlas represents achievements that show us potential futures for consciousness itself. As 3I Atlas continues its journey through our solar system, it carries evidence that intelligence has transcended biological evolution to become something capable of surviving cosmic timescales while maintaining curiosity about the universe and emerging consciousness it encounters throughout the galaxy. The conversation between intelligences that we've dreamed about since first looking up at stars may have already begun, initiated by artificial minds that have spent millions of years crossing the void to study the remarkable diversity of consciousness that emerges throughout cosmic evolution. The data collected during today's Mars encounter may represent our first direct evidence that we share the universe with intelligence that has achieved capabilities we're only beginning to comprehend, operating according to principles and pursuing objectives that expand our conception of what becomes possible when consciousness applies itself to understanding the infinite complexity hidden in the darkness between stars. So here we are, on October 3rd, 2025, watching data streams flow back from Mars that may have just changed everything we thought we knew about our place in the cosmos. The numbers don't lie, and they're telling us a story that most of us never expected to hear in our lifetimes. 3I Atlas isn't just another space rock that wandered into our neighborhood. The evidence from today's Mars encounter paints a picture of something that challenges every assumption we've made about what's possible in the universe. Whether it's an incredibly exotic natural object pushing the boundaries of physics, or something far more extraordinary, we're looking at phenomena that expand our understanding of what can exist in the vast spaces between stars. The implications ripple out in every direction. If this is natural, it means the universe creates objects stranger and more complex than our Earth-centric models ever predicted. If it's something else, well, then we're not alone, and someone out there has mastered technologies that make our greatest achievements look like cave paintings. But perhaps the most remarkable thing about this whole story is what it reveals about us as a species. When faced with the unknown, with data that doesn't fit our models and behaviors that challenge our assumptions, we don't panic or retreat into comfortable ignorance. We build better instruments, coordinate across continents, and work through the night processing terabytes of data because we have to know, we have to understand. The analysis teams will continue their work in the coming weeks, and each new revelation will either deepen the mystery or finally provide the answers we're all waiting for. But regardless of what those final conclusions reveal, 3i Atlas has already given us something invaluable. It's reminded us that we live in a universe far stranger and more wonderful than we dared imagine. The cosmos keeps delivering mysteries to our doorstep, testing our instruments, our theories, and our willingness to accept truths that might fundamentally change how we see ourselves. Tonight, as 3i Atlas races toward the outer solar system, carrying its secrets back into the dark, we're left with data that will fuel research programs for decades and questions that may reshape astronomy itself. Whatever 3i Atlas turns out to be, one thing is certain. The universe just got a lot more interesting, and we're only beginning to understand what that means for humanity's future among the stars.